the vast darkness of space, a single galaxy burns bright enough to rewrite everything we thought we knew about cosmic history. This galaxy existed when our universe was barely 290 million years old, just 2% of its current age. But this ancient light carries secrets that challenge our deepest theories about how galaxies form, how quickly stars can ignite, and whether the universe itself might be hiding inside something unimaginably vast. From impossible brightness to missing black holes. From chemical fingerprints that should not exist to theories that place our entire reality within a cosmic prison. Prepare yourselves. Deep in the constellation Fornax, astronomers discovered something that should not exist. A galaxy that burns with the light of hundreds of millions of suns. Yet it formed when the universe was barely out of its infancy. Named Jade's GS Z14-0. This cosmic lighthouse shattered every distance record we had ever set. At a redshift of 1432, it dates back to less than 300 million years after the Big Bang, pushing our view deeper into time than ever before. To understand how extraordinary this discovery truly is, picture the universe as a 13-year-old child. This galaxy would have existed when that child was barely 3 months old. The light we see today began its journey across 13.5 billion years of expanding space. Stretched and reddened by the universe's own growth, the James Webb Space Telescope observed this galaxy for almost 10 hours using its near-infrared spectrograph. And when scientists first processed the spectrum, they knew they were looking at something unprecedented. The previous record holder, another galaxy discovered just years earlier, suddenly seemed almost modern in comparison. But distance alone was not what made this discovery so startling. Jade's GS Z14-0 is over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from emission near a growing supermassive black hole. For a galaxy this early in cosmic history, such a size defies our expectations. Imagine trying to build a massive city in just the first few days after breaking ground on an empty plot of land. That is essentially what this galaxy accomplished in cosmic terms. The building blocks of matter had barely had time to cool and clump together when this galaxy was already blazing across the early universe. The source was surprisingly bright, which we wouldn't expect for such a distant galaxy. Astronomers admitted, in the infant universe, galaxies should be small, faint, and struggling to form their first stars. Instead, this ancient giant glows with an intensity that rivals much younger, more mature galaxies we observe in our cosmic neighborhood. The discovery forced scientists to question fundamental assumptions about galaxy formation. How could something so massive and luminous exist so early? What processes could have assembled so much matter and ignited so many stars in such a remarkably short time? Its age, size, and luminosity added to a growing body of evidence that current theories of early star and galaxy formation are incomplete. This single point of light in the darkness was telling us that the early universe was far more active and dynamic than our models had predicted. When astronomers split the light from Jade's GS Z14-0 into its component wavelengths, they uncovered a chemical signature that challenged everything we knew about the early universe. The galaxy was rich in nitrogen, unusually rich for such an ancient object. This discovery was like finding a sophisticated wine cellar in a house that was supposedly built yesterday. Nitrogen is not a primordial element that existed at the universe's birth. Instead, it must be forged inside stars and scattered into space when those stars die. Jade's analysis indicates that the brightness of the source, implied by the mere observation, is above what would be extrapolated from the measurements by the other Webb instruments, indicating the presence of strong ionized gas emission in the galaxy in the form of bright emission lines from hydrogen and oxygen. But nitrogen presented an even deeper puzzle. In the cosmic timeline, hydrogen and helium were the only elements present after the Big Bang. Every other element, from carbon to iron to nitrogen, had to be manufactured inside stellar furnaces over millions or billions of years. Stars live, burn through their nuclear fuel, and die, scattering these newly created elements into space, where they can be incorporated into the next generation of stars. This process takes time, lots of time. For a galaxy to be nitrogen-rich just 290 million years after the Big Bang, multiple generations of massive stars would have had to live entire life cycles, die in spectacular explosions, and seed the surrounding space with their chemical products. Imagine trying to find evidence of a great-grandparent's recipes in a cookbook written on the day a family first settled in a new country. The presence of complex, refined ingredients would suggest that many generations had already passed, even if the official records claimed otherwise. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that Jade's GS Z14-0 is forming stars in extremely dense environments. The connection between this ancient galaxy and the oldest stellar populations in our own cosmic neighborhood implied that rapid, intense star formation was occurring under conditions we had not fully understood. The nitrogen abundance pointed to what astronomers call chemical evolution happening at an accelerated pace. Normally, this process unfolds over billions of years as successive generations of stars gradually enrich their surroundings with heavier elements. But Jade's GS Z14-0 appeared to have compressed this timeline dramatically. That means galaxy evolution may have started much earlier than we thought. If massive stars were forming, living, and dying fast enough to produce significant nitrogen enrichment within the first few 100 million years of cosmic history, then the universe was far more active in its youth than our models predicted. The chemical fingerprints suggested that this galaxy was not a pristine, first-generation object, but rather the product of an already complex stellar ecosystem. Jade's GS Z14-0 was supposed to be an impossible outlier, a cosmic fluke that defied all expectations about the early universe. Instead, it opened the door to a much larger mystery. Given the relatively small region of the sky that we searched to find Jade's GS Z14-0, its discovery has profound implications for the predicted number of bright galaxies we see in the early universe. If such luminous objects could be found in a tiny patch of sky, how many more were waiting to be discovered across the vast cosmic landscape? Think of it like finding a bustling city while exploring what you thought was an empty wilderness. The discovery would immediately raise questions about how many other cities might exist in unexplored regions. Astronomers faced a similar situation as they realized that bright early galaxies might be far more common than anyone had imagined. Since its science observations began in July 2022, the JWST has discovered a series of increasingly distant ancient galaxies. Each new discovery pushed the boundaries further back in time, but also revealed that the early universe was populated with objects that should not have existed yet. The James Webb Space Telescope had only surveyed a minute fraction of the entire sky, yet it was consistently finding these bright, ancient galaxies. Statistical analysis suggested that there could be hundreds or even thousands of similar objects scattered across the cosmic deep field, each one representing a challenge to our understanding of early galaxy formation. Astronomers have used data from NASA's James Webb Space Telescope early release observations and discovered 87 galaxies that could be the earliest known galaxies in the universe. This growing population of ancient, bright objects was rewriting the cosmic census. Previous models had predicted that early galaxies would be small, faint, and rare. universe should have been a relatively quiet place in its first few 100 million years, with star formation proceeding slowly and inefficiently. Instead, astronomers were finding evidence of vigorous stellar nurseries operating at full capacity when the cosmos was still in its infancy. These ancient, bright galaxies, sometimes called little red dots, are popping up across JWST's surveys. The nickname little red dots came from their appearance in early telescope images. But these objects were proving to be anything but insignificant. Each new discovery added weight to the growing realization that the early universe was far more active and structured than theoretical predictions had suggested. If bright galaxies were common in the cosmic dawn, it meant that the processes of star formation, element creation, and galactic assembly had proceeded much more rapidly than anyone had thought possible. It is likely that astronomers will find many such luminous galaxies, possibly at even earlier times, over the next decade with Webb. The James Webb Space Telescope was just beginning to explore the deepest reaches of space and time. Every major scientific theory rests on a foundation of carefully constructed models that predict how the universe should behave. When observations consistently contradict these predictions, scientists face a fundamental choice: modify the models or question whether something deeper is wrong with our understanding of reality itself. Current theories of early star and galaxy formation are incomplete. The discovery of Jade's GS Z14-0 and its bright companions was forcing astronomers to confront this uncomfortable truth. Decades of theoretical work had painted a picture of gradual cosmic evolution, but the universe was revealing a much more dramatic and rapid development. The spectroscopic confirmation of this source indicates the existence of many similar galaxies, particularly when considering the relatively small survey area of Jade's. This was not just one anomalous object that could be explained away as a special case. It was evidence of a systematic underestimation of how quickly the early universe could assemble complex structures. Consider a computer simulation designed to predict how a city will grow over time. If the simulation consistently predicts slow, gradual development, but satellite images reveal massive skyscrapers appearing in just the first few months, the underlying assumptions about construction rates and urban planning would need to be completely reconsidered. Cosmological models faced a similar crisis. The halo mass threshold required to yield a fixed moving abundance varies as the inverse sixth power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to host such massive galaxies should have been extremely rare at such early times. Dark matter halos provide the gravitational scaffolding upon which galaxies form. These invisible structures must grow to a sufficient size before they can begin efficiently converting gas into stars. According to standard models, the early universe should not have had enough time to grow halos massive enough to support the bright galaxies Webb was discovering. Jade's GS Z14-0 represents a fascinating, yet very challenging test case for the scenario that astronomers had developed to explain galaxy formation. The galaxy exhibited properties that stretched multiple theoretical frameworks to their breaking points. The crisis extended beyond just galaxy formation models. If the early universe was more structured and active than predicted, it might indicate problems with our understanding of dark matter, dark energy, or even the fundamental physics governing cosmic expansion. If galaxies like Jade's GS Z14-0 existed in greater numbers, formed stars faster, and were chemically richer than we thought possible, what else are we missing? This question hung over the astronomical community like a storm cloud, suggesting that the discoveries might be symptoms of much deeper misunderstandings. Some theoretical physicists began to propose radical solutions. Perhaps the universe itself was not what it seemed to be. Perhaps perhaps the very stage upon which cosmic evolution played out, was fundamentally different from what we had assumed. The discovery of Jade's GS Z14-0 marked the beginning of a cosmic treasure hunt that would reshape our understanding of the universe's earliest chapters. The astronomers agree that JWST's power has not yet reached its limits. None of them would be surprised if the telescope unveils a new redshift record within the year. The James Webb Space Telescope was operating like a time machine, systematically pushing back the boundaries of observable cosmic history. Astronomers realized they were standing at the edge of a new frontier. Every observation session brought the possibility of finding even more distant, even more impossible galaxies. This specific area Jades has been studying is pretty small. There are larger areas of the sky that have yet to be explored that maybe have even brighter and more distant galaxies. Picture archaeologists who had spent decades carefully excavating what they thought was a small, ancient settlement, only to discover that they were standing on the edge of a vast, buried metropolis. The scope of their task had suddenly expanded beyond anything they had imagined. Jade's GS C14-0 was the record holder at a redshift of 1432, but now another ancient, bright galaxy has been found at a redshift of 14,444, less than a year after the first discovery. An even more distant galaxy had been confirmed, pushing the cosmic frontier back by another 10 million years. This new record holder demonstrated that the pattern of unexpectedly bright early galaxies was not a fluke. This finding is surprising because astronomers expected to find very few galaxies at such a high redshift. Each new discovery reinforced the growing evidence that the early universe was far more active than anyone had predicted. The search was expanding beyond single telescope observations. Teams of astronomers around the world were coordinating efforts, sharing data, and developing new techniques to probe even deeper into cosmic time. Advanced computer algorithms were being trained to identify candidate distant galaxies in the vast data sets that Webb was collecting. Later this decade, the Nancy Grace Roman Space Telescope will join JWST in scanning the early universe. Roman will cover much larger areas of the sky with incredible detail. The Roman telescope would complement Webb's deep but narrow view with a wider survey capability, potentially discovering hundreds or thousands of ancient, bright galaxies. Together, these space telescopes would create the most comprehensive census of the early universe ever attempted. Every new galaxy discovered would add another piece to the puzzle of how cosmic structures formed and evolved during the universe's youth. But the implications extended far beyond simple discovery. Each ancient galaxy was a laboratory for testing our understanding of physics under extreme conditions. The densities, temperatures, and energy scales present during the formation of these early objects pushed matter to its limits. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away, while astronomers struggled to understand why ancient galaxies were brighter and more numerous than expected. A completely different mystery was emerging from the data. New research has uncovered an intriguing mystery that the majority of galaxies appear to be rotating in the same direction across vast regions of space. Galaxies seem to be spinning in a coordinated pattern, as if responding to some universal influence. In a truly random universe, galaxy rotations should be roughly evenly split between clockwise and counterclockwise directions when viewed from our perspective. Imagine throwing thousands of coins into the air and finding that 70% land heads up. Such a result would immediately suggest that either the coins are weighted or some external force is influencing their behavior. This is significant because in a truly random universe, galaxy rotations should be roughly evenly split between two directions. The discovery of a preferential rotation challenged one of the most fundamental assumptions in cosmology, that the universe is isotropic and homogeneous on large scales. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. The implications were staggering. If the universe has a preferred direction or axis, it would mean that space itself might have properties we had never suspected, like discovering that what appeared to be a perfectly smooth sphere actually has subtle ridges or patterns that influence everything that moves across its surface. Some researchers propose that this cosmic choreography might be evidence of rotation in the universe itself. If space-time possesses some form of overall angular momentum, it could impart a slight preference for rotational direction to the galaxies that form within it. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. The discovery was opening doors to exotic physics that operated on scales beyond anything we could directly test in laboratories. Alternative explanations were equally mind-bending. Perhaps the observed patterns were fossil remnants of processes that occurred during cosmic inflation, the theoretical period of rapid expansion that occurred in the universe's first fraction of a second. Or maybe they reflected the influence of dark matter structures that we could not directly observe. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. Some physicists were beginning to wonder whether the coordinated galactic rotation might be evidence that our entire universe exists within such a boundary. Deep within the mathematics of general relativity lies a possibility so strange that most physicists had dismissed it as a mere curiosity. What if our entire universe exists inside a black hole? Some scientists interpreting the data have proposed something bold, that our entire universe might exist inside a black hole. This radical hypothesis, known as black hole cosmology, suggests that everything we observe, from distant galaxies to our own solar system, exists within the event horizon of a massive black hole in a larger parent universe. The theory emerged from attempts to reconcile the strange properties of the Big Bang with the physics of black holes. The Standard Model tells us that the universe began as a singularity, a point of infinite density, just like the center of a black hole. Both scenarios involve matter compressed to impossible densities under the influence of extreme gravitational fields. If our universe is actually the interior of a black hole that formed in a larger parent universe, it would mean that the Big Bang was not an explosion in empty space, but rather the moment matter collapsed into a black hole, creating a new universe inside. This would transform our understanding of cosmic origins from a mysterious beginning to a natural consequence of gravitational collapse in a higher dimensional reality. Consider the mathematical elegance of this possibility. Every property that makes our universe seem special, from its expansion rate to the values of the fundamental constants, could be natural consequences of existing within a black hole's interior. The apparent fine-tuning that allows complex structures like stars and galaxies to form might simply reflect the physics of black hole formation. Each and every black hole in our universe could be the doorway to another baby universe. This would create a fractal cosmos, where universes give birth to universes through the formation of black holes, each new universe potentially developing its own physics and evolutionary timeline. The theory offered elegant explanations for several cosmic puzzles. Black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. The connection between entropy and information could help resolve paradoxes about what happens to information that falls into black holes. Even more intriguingly, the coordinated rotation of galaxies that astronomers were discovering could be a natural consequence of existing within a rotating black hole. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce, where the core rebounds and expands outward, potentially giving rise to a new universe inside. The mathematics suggested that quantum effects might prevent the formation of true singularities, causing collapsing matter to rebound and expand into new space-time regions. The scientists continued by adding that the rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. If our universe truly exists within a black hole, then every black hole we observe might be a doorway to an entirely new cosmos, complete with its own physics, planets, and perhaps even life. This theory would drastically change our understanding of cosmic origins, suggesting that the cycle of universes is an ongoing, self-replicating process. Instead of a single universe that appeared from nothing, we might inhabit one branch of an infinite cosmic tree, where each black hole represents both an ending and a beginning. Picture a vast cosmic ecosystem where universes reproduce through gravitational collapse. Just as biological organisms pass genetic information to their offspring, parent universes might transmit physical laws and constants to their cosmic children through the formation of black holes. This could explain why the fundamental forces in our universe seem precisely calibrated to allow complex structures to emerge. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. Universes with physics that promote stable star formation and complex chemistry would be more likely to produce the black holes necessary for cosmic reproduction. The implications were staggering. Every time a massive star collapses in our universe, it might be giving birth to a new cosmos containing billions of galaxies, each with their own planets and possibilities for life. The stellar death that marks an ending in our universe could simultaneously represent the Big Bang of another reality. This cosmic reproduction cycle would operate on timescales that dwarf biological evolution. While life on Earth has evolved over billions of years, cosmic evolution would unfold over trillions of generations of universe formation and development. Each new universe would be a cosmic experiment, testing slightly different combinations of physical laws and constants. The black hole universe theory also offered a potential resolution to the horizon problem in cosmology. Our universe appears remarkably uniform in temperature and structure across regions that should never have been in causal contact. If our cosmos began as the interior of a pre-existing black hole, this uniformity could be inherited from the parent universe's properties. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. Quantum mechanical effects operating at the smallest scales might create the cosmic bounce that transforms gravitational collapse into universal expansion. The mathematics of this process remained challenging, but the conceptual framework was elegant. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. Our Big Bang would be just one moment in an endless cycle of cosmic death and rebirth. Standing at the edge of cosmic understanding, astronomers find themselves equipped with tools powerful enough to peer back to the very dawn of time, yet humble enough to realize how much remains unknown. If it survives repeated cancellation threats, The Roman Space Telescope should reveal hundreds more of these types of galaxies. The future of cosmic archaeology depends not just on technological advancement, but on humanity's commitment to exploring the deepest questions about our existence. The Nancy Grace Roman Space Telescope, with its wide field capabilities, will complement the James Webb Space Telescope's deep but narrow view. Together, these instruments will conduct the most comprehensive survey of the early universe ever attempted. Where Webb finds individual ancient galaxies with exquisite detail, Roman will map their distribution across vast regions of space. A larger data set is always desirable and would help solidify some of these findings, or maybe introduce new mysteries. Science advances through the accumulation of evidence, but it also thrives on the discovery of new puzzles that challenge existing theories. The statistical power of hundreds or thousands of early galaxy observations will allow astronomers to test whether the current discoveries represent genuine departures from theoretical predictions or simply the extreme tail of expected distributions. More data will either confirm that galaxy formation proceeded much more rapidly than predicted or reveal new physics operating in the early universe. But the implications extend far beyond astronomy. The universe is turning out to be far stranger than we ever imagined. And the uneven galactic rotations will likely prompt astrophysicists to reassess certain aspects of our understanding of the universe. Each new discovery forces us to question assumptions we thought were rock solid. The coordinated rotation of galaxies across cosmic distances might indeed point to our universe existing within a larger structure. Or it might reveal new physics operating on scales we can barely comprehend. Either possibility would fundamentally change how we understand our place in the cosmic hierarchy. Maybe some earlier measurements of our universe are incorrect, especially the speed at which the Milky Way galaxy rotates. Sometimes, revolutionary discoveries turn out to have more mundane explanations, but the process of investigating them always advances our knowledge. Future observations will probe even deeper into cosmic time, perhaps eventually reaching the era when the very first stars ignited in the primordial darkness. These population 3 stars, composed only of hydrogen and helium, would have been massive giants that lived brief but spectacular lives, seeding space with the heavier elements necessary for planets and life. Scientists using Webb to study GNZ11 have also uncovered some tantalizing evidence for the existence of population 3 stars nestled in the outskirts of this remote galaxy. The discovery of these primordial stars would complete our picture of how the universe transitioned from simplicity to complexity. Supermassive black holes, with masses millions or billions of times greater than our sun, typically power the brightest objects in the universe. These cosmic engines devour gas and dust, heating material to millions of degrees and launching it outward in brilliant jets of plasma. When astronomers spot an exceptionally bright galaxy, they usually expect to find one of these giants lurking at its center. Jade's GS Z14-0 defied this expectation completely. From the images, the source is found to be over 1,600 light-years across, proving that the light we see is coming mostly from young stars and not from emission near a growing supermassive black hole. The galaxy's brightness was not the product of a feeding black hole, but rather an explosive nursery of newborn stars. This absence created a cosmic puzzle. Most galaxies that shine this brightly rely on the intense radiation generated by matter spiraling into a supermassive black hole. These black holes act like cosmic lighthouses, often outshining all the stars in their host galaxies combined. But Jade's GS Z14-0 was generating its tremendous luminosity through pure stellar formation. Think of it like discovering a medieval village that somehow produces the same amount of light as a modern city, but without any electrical power. The village would need to have an impossibly large number of torches and fires burning simultaneously. Similarly, this ancient galaxy needed to be forming stars at a rate that seemed almost impossible for its era. The galaxy has a star formation rate, averaged over the last 10 million years, of approximately 22 solar masses per year. That means every single year, this galaxy converts material equivalent to 22 suns into newborn stars. For such a young cosmic age, this rate represents a stellar baby boom of unprecedented proportions. The implications stretch far beyond this single galaxy. Supermassive black holes are thought to play crucial roles in regulating star formation throughout their host galaxies. They can both trigger star birth by compressing gas clouds and halt it by blowing material away with powerful winds. Without a central black hole, how is this galaxy managing to form stars so efficiently? Even more puzzling, most theoretical models suggest that supermassive black holes and their host galaxies grow together over cosmic time. The absence of a detectable black hole in such a massive early galaxy challenged this fundamental relationship. All of these observations, together, tell us that Jade's GS-Z14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe. It was operating by rules we had not yet discovered, hidden in the outskirts of ancient galaxies. Astronomers are searching for the universe's very first stars. These elusive objects, known as Population 3 stars, would have been the cosmic pioneers that brought light to a universe filled only with hydrogen and helium. No definitive detection of such stars has ever been made. But scientists know they must exist. Now, with Webb, their discovery seems closer than ever before. Scientists using Webb to study another ancient galaxy have also uncovered some tantalizing evidence for the existence of Population 3 stars nestled in the outskirts of this remote galaxy. These primordial giants would have been fundamentally different from any star we observe today, composed entirely of the simplest elements forged during the Big Bang. Picture the universe in its first 100 million years as a vast, dark ocean punctuated by islands of light. Population 3 stars would have been these first beacons, massive beyond anything we see in the modern cosmos. Without heavier elements to help them radiate energy efficiently, these stars would have grown to enormous sizes, perhaps 50 to 100 times more massive than our Sun. Their lives would have been spectacular, but brief, burning through their nuclear fuel in just a few million years. These stellar giants would have ended their existence in catastrophic explosions that scattered the first heavy elements across space. Carbon, oxygen, nitrogen, and iron, forged in their nuclear furnaces, would become the building blocks for the next generation of stars, and eventually for planets and life itself. The search for Population 3 stars represents one of astronomy's greatest challenges. These objects existed so long ago that their light has been traveling for over 13 billion years to reach us. Even the most powerful telescopes struggle to detect individual stars at such extreme distances. But Webb's infrared vision offers new hope. When Population 3 stars exploded as supernovas, they would have created distinctive signatures in the surrounding gas clouds. These fingerprints might still be visible today, encoded in the light from galaxies that formed in regions enriched by the first stellar explosions. Looking deeply into space and time, two teams using NASA's James Webb Space Telescope have studied the exceptionally luminous galaxy, which existed when our 13.5-billion-year-old universe was only about 430 million years old. This galaxy shows chemical patterns that might reflect the influence of population 3 stellar explosions. A second team used Webb's near-infrared spectrograph to find a gaseous clump of helium in the halo surrounding this ancient galaxy. Pure helium clouds are exactly what astronomers would expect to find if population 3 stars had recently exploded nearby, seeding space with their nuclear products while leaving behind pockets of pristine, primordial gas. The discovery of these cosmic fossils would complete our understanding of how the universe transitioned from darkness to light. Population 3 stars were the match that lit the cosmic candle, beginning the long chain of stellar evolution that eventually led to our solar system. Each ancient galaxy discovered by Webb brings us closer to finding direct evidence of these first stars. Every element heavier than hydrogen and helium tells a tale of stellar alchemy, of massive stars that lived, died, and scattered their nuclear products across space. This cosmic recycling program transformed a universe of simple gases into one capable of supporting rocky planets, organic molecules, and eventually, life itself. When astronomers examine the light from Jade's GS Z14-0 and other ancient galaxies, they are reading the chemical diary of the early universe. Each emission line in their spectra represents a different element, and the relative intensities reveal how much of each element was present when that light was emitted. The nitrogen abundance in these early galaxies presents a cosmic puzzle that challenges our understanding of stellar evolution timescales. Nitrogen is primarily produced inside intermediate mass stars through a complex series of nuclear reactions that typically require hundreds of millions of years to complete. Yet these galaxies existed when the universe was barely 300 million years old. For them to show significant nitrogen enrichment, stellar evolution must have proceeded much more rapidly than our current models predict, or entirely different physical processes were at work in the early cosmic environment. This chemical fingerprint matches what we see in some of the oldest star clusters orbiting the Milky Way, suggesting that similar physical conditions existed both in the early universe and in the dense environments where globular clusters form. The connection implies that we might be observing universal principles of star formation operating under extreme conditions. The implications extend far beyond individual galaxies. If chemical evolution proceeded rapidly throughout the early universe, it would mean that the building blocks for complex chemistry became available much sooner than previously thought. Rocky planets could have formed earlier. Organic molecules could have emerged sooner. And the window for life to develop would have opened billions of years ahead of schedule. Consider the profound philosophical implications. If the universe became chemically mature much earlier than we believed, then Earth-like worlds, and potentially life itself, might have had far more time to develop and evolve. We might be late arrivals to a cosmic party that has been ongoing for much longer than anyone imagined. The rapid chemical enrichment also suggests that feedback processes between stars and their surrounding gas operated differently in the early universe. Stellar winds and supernova explosions would have mixed freshly synthesized elements through space more efficiently, accelerating the pace of cosmic evolution. Furthermore, as noticed by recent studies, these morphological differences are reflected in chemical abundance patterns, signaling a deeper connection between galaxy structure and evolutionary pathways. Compact galaxies tend to show different chemical signatures than extended ones, suggesting that physical size and chemical evolution are intimately linked. The universe was conducting chemistry experiments on a cosmic scale, testing different combinations of stellar masses, formation rates, and environmental conditions. Each ancient galaxy represents a different outcome of these experiments. Invisible scaffolding shapes everything we see in the universe. Yet the discovery of impossibly early, massive galaxies suggests this cosmic architecture might work differently than we thought. Dark matter. the mysterious substance that comprises over 80% of all matter in the universe, provides the gravitational framework upon which galaxies form. According to our best theories, ordinary matter falls into dark matter halos, accumulating until it reaches the critical density needed to ignite star formation. This process should take time, lots of time. Dark matter halos must grow through countless mergers and accretion events before they become massive enough to host the bright galaxies that Webb is discovering. The standard model of cosmic structure formation predicts that truly massive halos should have been extremely rare in the first few 100 million years after the Big Bang. Yet JADE's GS-Z14-0 and its companions exist in apparent defiance of these predictions. The halo mass threshold required to yield a fixed come-moving abundance varies as the inverse sixth power of 1 plus redshift for this region of mass and redshift. In simpler terms, the dark matter structures needed to support such massive early galaxies should have been vanishingly rare. Think of it like finding skyscrapers in a city that was supposedly founded just last week. The construction requires not just time, but also the development of sophisticated infrastructure, supply chains, and engineering expertise. Similarly, massive galaxies require mature dark matter halos that should not have existed so early in cosmic history. From a theoretical simulation, we estimate that the probability of finding halos massive enough to host these bright early galaxies was incredibly low. The simulations suggest we should have found perhaps one such object in the entire observable universe, not dozens scattered across Webb's relatively small survey areas. This discrepancy points to several possible explanations, each with profound implications for our understanding of cosmic evolution. Perhaps dark matter behaves differently than we assumed, interacting with itself or with ordinary matter in ways that accelerate halo formation. Or maybe the relationship between halo mass and galaxy brightness is not what our models predict. Alternative theories propose that dark matter might have additional properties that become important in the extreme conditions of the early universe. Self-interacting dark matter, for instance, could undergo rapid collapse and rebound cycles that efficiently concentrate mass into the cores of halos. Another possibility is that early star formation was far more efficient than current models suggest. If the first stars could form with much less dark matter support than is required today, then bright galaxies could appear in smaller halos that were more common in the early universe. The puzzle deepens when we consider that these early galaxies show evidence of multiple generations of stellar evolution. Not only did they form earlier than expected, but they also evolved faster, cycling through stellar birth and death at an accelerated pace that compressed billions of years of evolution into a few 100 million. In the cosmic dance between stars and galaxies, energy flows in both directions, creating feedback loops that should regulate and limit how quickly galaxies can grow. When massive stars explode as supernovas, they release tremendous amounts of energy that heats the surrounding gas and blows it away from the galaxy. This process, known as stellar feedback, acts like a cosmic thermostat, preventing galaxies from forming stars too quickly and burning through their gas reserves. Similarly, when gas falls into supermassive black holes, it generates powerful winds and jets that can clear entire galaxies of star-forming material. These feedback mechanisms are thought to be essential for explaining why galaxies do not convert all of their available gas into stars within the first few million years of their existence. Yet the ancient galaxies discovered by Webb seem to have bypassed these cosmic speed limits entirely. JADE's GS-Z14-0 shows evidence of vigorous star formation occurring at rates that should have triggered feedback processes strong enough to shut down further stellar birth. The galaxy exhibits properties that stretched multiple theoretical frameworks to their breaking points. Its high star formation rate, combined with its large stellar mass, suggests that feedback mechanisms were either much weaker in the early universe, or that these galaxies had access to continuous supplies of fresh gas to fuel their incredible growth. Consider the energy budget involved. Every time a massive star explodes, it releases energy equivalent to our sun's entire lifetime output in just a few seconds. Multiple supernovas exploding within a small galaxy should create a devastating storm of hot gas and radiation that prevents new stars from forming for millions of years. But these early galaxies appear to have weathered such cosmic storms without interruption. Some theoretical models suggest that the dense environment of the early universe might have allowed galaxies to retain their gas despite energetic feedback processes. The rapid chemical enrichment observed in these galaxies provides additional evidence that stellar feedback was not effectively removing freshly synthesized elements from star-forming regions. Instead of being blown away by stellar winds, heavy elements were apparently retained and incorporated into subsequent generations of stars. This retention of metals and gas implies that early galaxies were more efficient at converting raw materials into stars than their modern counterparts. The physics of star formation itself might have operated differently when the universe was young and dense. Another possibility is that these galaxies were fed by continuous streams of pristine gas falling in from the cosmic web. If the accretion rate was high enough, it could overwhelm the feedback processes and maintain a steady rate of star formation despite ongoing stellar explosions. The crisis in feedback theory extends beyond individual galaxies to cosmic evolution as a whole. If early galaxies could grow without the regulatory mechanisms that govern modern star formation, then the entire timeline of cosmic structure formation might need to be reconsidered. Stretching across billions of light years, an invisible network of dark matter filaments connects galaxies throughout the universe, forming the cosmic web that defines large-scale structure. This vast scaffolding channels gas and dark matter along preferred pathways, feeding material to galaxies at the intersections where filaments meet. The cosmic web grows gradually over time, with the most massive structures forming at the nodes where multiple filaments converge. According to standard models, the early universe should have had only the most rudimentary web structure. The first few 100 million years after the Big Bang would have been dominated by small-scale fluctuations, with large-scale organization developing slowly as gravity amplified the tiny density variations left over from cosmic inflation. Yet the discovery of numerous bright galaxies at extreme distances suggests that the cosmic web was already remarkably well developed when the universe was barely 300 million years old. These galaxies appear to be located at the major intersections of dark matter filaments, implying that large-scale structure formation proceeded much more rapidly than predicted. If the universe does have a preferred direction, it could point to unknown physics at play, possibly related to the way our universe formed inside a black hole, or how fundamental forces interact on the grandest scales. Studies of large-scale cosmic structures suggest a certain alignment in the way galaxies are distributed and move, rather than being entirely random. This cosmic anisotropy challenges the widely accepted cosmological principle, which assumes the universe is isotropic and homogeneous on large scales. Picture the cosmic web as a three-dimensional spiderweb spanning the entire observable universe. In the standard picture, this web should have been sparse and incomplete during the cosmic dawn, with only small sections connected to each other. Instead, observations suggest that the major highways of the cosmic web were already in place, efficiently channeling material to the galaxy formation sites. The implications are staggering. If large-scale structure formation proceeded much faster than our models predict, it might indicate that dark matter and dark energy behave differently than we assume, or that additional physical processes were at work during the universe's earliest epochs. Alternative explanations invoke exotic physics operating during cosmic inflation. Perhaps the quantum fluctuations that seeded cosmic structure were not as random as we believed, but instead carried subtle patterns that accelerated the formation of these large-scale networks. Another possibility is that the cosmic web itself influences galaxy formation in ways we have not fully understood. Rather than simply providing the scaffolding for galaxy assembly, the web might actively channel energy and matter in patterns that enhance the efficiency of star formation. The discovery of bright early galaxies at what appear to be the nodes of the cosmic web suggests that the relationship between large-scale structure and galaxy formation was already well established when the universe was remarkably young. One of cosmology's most enduring puzzles concerns how the universe achieved such remarkable uniformity across regions that should never have been in causal contact. The cosmic microwave background radiation, the afterglow of the Big Bang, shows the same temperature to within 1 part in 100,000 across the entire sky. This uniformity extends to regions separated by distances so vast that light has not had time to travel between them since the universe began. How can regions that have never exchanged information display such identical properties? This horizon problem has plagued cosmologists for decades, leading to the development of the cosmic inflation theory as a proposed solution. Inflation suggests that the universe underwent a brief period of exponential expansion in its first fraction of a second, stretching tiny, causally connected regions to cosmic scales. This would explain how distant parts of the universe share the same temperature and other properties. But the discovery of impossibly bright and massive galaxies in the cosmic dawn adds a new dimension to the horizon problem. These objects appear to have formed too quickly and grown too large for the available time, suggesting that the early universe was more interconnected and organized than the standard model allows. If our cosmos began as the interior of a pre-existing black hole, this uniformity could be inherited from the parent universe's properties. The horizon problem would dissolve because our universe would have inherited its uniform properties from a larger, already connected system. This black hole cosmology offers an elegant resolution to several cosmic puzzles simultaneously. The Big Bang would not represent the beginning of time, but rather a phase transition from gravitational collapse to expansion, carrying forward the organized properties of the parent universe. Consider the implications for early galaxy formation. If our universe inherited large-scale structure from its parent, then the cosmic web could have been partially assembled from the very beginning. This would explain how massive galaxies could form so quickly, in apparent violation of the bottom-up structure formation models. The coordinated rotation of galaxies across cosmic distances might be another inherited property, reflecting an angular momentum present in the parent universe at the time of black hole formation. Instead of emerging randomly from quantum fluctuations, large-scale patterns could be the fossil remnants of the parent cosmos. Recent observations of cosmic anisotropy, where galaxies show preferred orientations across vast regions of space, support the idea that the universe possesses large-scale, coherent properties that extend beyond what inflation alone can explain. If these patterns represent inherited characteristics from a parent universe, then many aspects of cosmic evolution that seem fine-tuned or improbable might actually be the natural consequences of our universe's nested origin within a larger cosmological system. The horizon problem, long considered evidence for exotic physics during cosmic inflation, might instead point toward an even more exotic possibility that our universe is one of countless cosmic offspring, each inheriting its properties from its parent through the formation of black holes. The fundamental constants of nature appear to be precisely calibrated to allow the existence of stars, planets, and life. A phenomenon that has puzzled scientists for generations. Change the strength of the strong nuclear force by just a few percent, and atomic nuclei would not be stable. Alter the ratio of the electron and proton masses slightly, and chemistry as we know it would be impossible. Adjust the cosmological constant that drives cosmic expansion, and galaxies might never form or might fly apart before stars can ignite. This apparent fine-tuning has led to intense debates about why our universe seems so perfectly suited for complexity in life. Some invoke the anthropic principle, arguing that we observe these values simply because we exist to observe them. Others propose the existence of multiple universes with different physical laws, making our life-friendly cosmos just one possibility among countless others. But the black hole universe theory offers a radically different perspective on this fine-tuning. This could also explain why the fundamental constants of nature appear fine-tuned for life, because black holes that create stable universes may be more likely to persist and reproduce through this process. Imagine cosmic evolution as a vast reproductive process, where universes that develop stable physics are more likely to create the black holes necessary for producing offspring universes. Over countless generations of cosmic reproduction, natural selection would favor physical constants that promote complexity, structure formation, and long-term stability. Universes with physics that promote stable star formation and complex chemistry would be more likely to produce the black holes necessary for cosmic reproduction. Those with constants that prevent galaxy formation or cause rapid collapse would be evolutionary dead ends, unable to propagate their physical laws to future generations. This cosmic natural selection would explain not only why our universe supports complexity, but also why the early galaxies discovered by Webb show such sophisticated chemical evolution. If our cosmos inherited its physics from a long lineage of successful parent universes, then rapid structure formation and efficient star formation might be deeply embedded characteristics. The fine-tuning paradox dissolves when viewed through this reproductive lens. Rather than being improbably perfect by chance or by design, our universe's properties would be the product of eons of cosmic evolution, refined through countless cycles of birth, development, and reproduction. Each generation of universes would inherit the successful physical constants of their parents, while potentially introducing small variations through the quantum mechanical processes operating during black hole formation. Over cosmic time, this would lead to the gradual optimization of physical laws for promoting complexity and longevity. The apparent youth and sophistication of the early galaxies fits naturally into this framework. If our universe descended from a long line of successful parent cosmos, it would have inherited not just fine-tuned constants, but also the capacity for rapid and efficient structure formation. Deep within the mathematics of black hole physics lies one of the most profound puzzles in modern science. What happens to information when it falls beyond the event horizon? According to quantum mechanics, information cannot be truly destroyed. Every particle, every quantum state, every bit of data about the physical world must be preserved in some form, even if it becomes impossible to access or decode. Yet black holes appear to violate this fundamental principle. When matter falls into a black hole, it seems to vanish from our universe completely, taking with it all the information about its quantum states, its history, and its properties. Stephen Hawking showed that black holes eventually evaporate through thermal radiation. But this radiation appears to carry no information about what fell in, creating an apparent paradox. But if our universe exists within a black hole, this paradox takes on a new and profound significance. Black holes are known to have immense entropy, which corresponds to the vast amount of information contained in our universe. Every star, planet, atom, and quantum state in our cosmos would contribute to the total information content stored within the black hole that contains us. This connection offers a potential resolution to the information paradox. Rather than being destroyed, the information that falls into black holes might give birth to new universes, each one encoding and preserving the quantum states that entered the black hole. The information would not be lost, but transformed into the initial conditions for a new cosmic system. Consider the staggering implications. Every black hole in our universe might contain not just compressed matter, but entire cosmological systems with their own galaxies, stars, and potentially life. The black holes we observe through our telescopes could be windows into countless other realities, each one as vast and complex as our own. This nested structure would create a cosmic library of unimaginable scale, where information is preserved across multiple levels of reality. The quantum states that fell into ancient black holes in parent universes might be encoded in the fundamental constants and initial conditions of our cosmos. The rapid formation of complex galaxies in our early universe might reflect information inherited from previous cosmic generations, rather than starting from simple initial conditions. Our universe could have begun with sophisticated organizational templates encoded in its basic structure. Each ancient galaxy discovered by Webb would represent not just early star formation, but the expression of cosmic information patterns inherited from parent universes. The chemical complexity, the structural organization, and the rapid evolution of these galaxies might be the manifestations of information processing operating on cosmological scales. If black holes preserve and transform information rather than destroying it, then every supermassive black hole in our universe serves as both an ending and a beginning. A cosmic recycling center where the information content of one reality becomes the foundation for new cosmic systems. At the heart of every black hole lies a mystery that challenges our understanding of space, time, and the fundamental nature of reality itself. Classical physics predicts that matter falling into a black hole will collapse into a singularity, a point of infinite density where the laws of physics break down completely. But quantum mechanics suggests a different fate, one that could transform cosmic death into cosmic birth. Some theories suggest that this twisting effect of space-time could generate a repulsive force at extremely high densities, potentially preventing singularities from forming. Instead of crushing matter into mathematical points, quantum effects might create a cosmic bounce that rebounds outward, giving birth to new, expanding universes. This quantum bounce mechanism operates through the inherent uncertainty principles that govern matter at the smallest scales. When particles are compressed to densities approaching the Planck scale, quantum fluctuations become so intense that they generate an outward pressure strong enough to halt and reverse the gravitational collapse. Picture a cosmic trampoline stretched to its absolute limit. Just as a ball dropped onto a trampoline will bounce back upward if the elastic force exceeds the downward momentum, matter collapsing into a black hole might rebound when quantum pressure overcomes the gravitational attraction. The scientists continued by adding that the rapid recoil after such a big bounce could be what has led to our expanding universe, an event we now refer to as the Big Bang. Instead of a singularity exploding from nothing, it could have been a rebirth from the core of a black hole in a parent universe. This mechanism would explain many of the puzzling features of our universe's early evolution. The rapid formation of large-scale structures, the sophisticated chemistry of early galaxies, and the apparent fine-tuning of physical constants could all be inherited characteristics from the parent universe. transmitted through the quantum bounce process. If true, this could mean that instead of collapsing into an infinitely small point, a black hole could experience a big bounce where the core rebounds and expands outward, potentially giving rise to a new universe inside. The process would conserve information while transforming it into new forms of cosmic organization. The quantum bounce would not be instantaneous, but might occur over cosmic timescales from the perspective of the new universe. What appears as the Big Bang and subsequent cosmic evolution to us might represent the gradual expansion following the quantum rebound of matter in a parent universe's black hole. This process could operate recursively, with each new universe capable of forming its own black holes and spawning additional cosmic offspring. The result would be an infinite, fractal structure where universes give birth to universes through cycles of collapse and quantum rebound. The early galaxies discovered by Webb might be direct evidence of this process at work. Their rapid formation and sophisticated properties could reflect the efficient transfer of organizational information from a parent to an offspring universe through the quantum bounce mechanism. Each black hole in our cosmos would be both a cosmic endpoint and a cosmic beginning, transforming the matter and information of our universe into the seeds of new realities through the mysterious quantum processes that operate at the intersection of gravity and quantum mechanics. If our universe exists within a black hole, then we must confront the possibility that reality is organized as an infinite hierarchy of nested cosmic systems. Every black hole we observe, from stellar mass objects to the supermassive giants at galaxy centers, could contain entire universes with their own galaxies, stars, planets, and potentially life. This would create a cosmic matryoshka doll of staggering proportions, where each level of reality contains countless sub-levels, extending downward into infinity. Consider the scale relationships involved. A supermassive black hole in our universe might contain a cosmos with billions of galaxies, each hosting billions of stars. Some of those stars would form their own black holes, creating additional layers of nested reality. The recursive structure would continue indefinitely, with no fundamental limit to the depth of cosmic organization. From our perspective, we occupy one specific level in this hierarchy. We can observe black holes that might contain entire universes, but we cannot directly communicate with or influence those nested realities. Similarly, if our universe exists within a black hole in a parent cosmos, the inhabitants of that larger reality would be unable to directly observe or interact with us. This cosmic hierarchy would operate according to fundamental principles of information, preservation, and transformation. Each level would inherit properties from its parent, while developing its own unique characteristics through the processes of cosmic evolution. The rapid formation of complex structures in our early universe might reflect our position in this hierarchy. If our cosmos inherited organizational templates from a parent universe, then sophisticated galaxy formation could proceed much more efficiently than models based on starting from simple initial conditions predict. Each new level of the hierarchy would represent a different scale of cosmic organization. Just as atoms combine to form molecules, molecules form cells, and cells form organisms. Universes might combine to form larger-scale structures that we cannot currently imagine or detect. The hierarchy might extend upward as well as downward. Our parent universe could itself be nested within an even larger cosmic system, which in turn exists within another level of reality. The ultimate structure could be infinite in both directions, with no fundamental top or bottom to the cosmic organization. This perspective transforms our understanding of cosmic significance. Rather than being isolated observers in a unique universe, We would be participants in an infinite network of cosmic consciousness, each level contributing to the overall complexity and information content of the universal hierarchy. The black holes we study with our telescopes would not be cosmic monsters devouring matter and energy, but cosmic wombs, nurturing new universes through their mysterious interiors. Each would represent a portal between different levels of reality, facilitating the flow of information and organization across cosmic scales. If every black hole contains a universe potentially harboring billions of intelligent civilizations, then consciousness might be far more abundant and significant in the cosmic scheme than we ever imagined. Rather than being rare accidents in an otherwise lifeless cosmos, thinking beings could be fundamental components of universal organization. Consider the information processing requirements of a nested universe system. Each level of the hierarchy would need to maintain, organize, and transform vast amounts of information as it inherits properties from parent universes and potentially gives birth to offspring cosmos. Consciousness might serve as the universe's method for processing and organizing this cosmic information. Intelligent civilizations could function as the universe's neurons, collecting data about their local cosmic environment, processing it through scientific observation and theoretical understanding, and potentially transmitting that information to other levels of the hierarchy through mechanisms we do not yet comprehend. The rapid development of complex structures in our early universe might reflect not just inherited physical organization, but inherited patterns of information processing. If parent universes develop sophisticated mechanisms for organizing matter and energy through the activities of conscious beings, these templates could be passed down to offspring cosmos. Each ancient galaxy discovered by Webb might represent not just stellar formation, but the emergence of information processing networks that will eventually give rise to consciousness and intelligence. The chemical complexity observed in these early systems provides the necessary building blocks for organic chemistry and, potentially, life. This perspective suggests that consciousness and cosmic evolution are intimately connected, rather than being separate phenomena. The development of intelligence and the organization of cosmic structure might be different aspects of the same fundamental process of universal information integration. The coordinated rotation of galaxies across vast distances might reflect large-scale information processing operating on cosmic scales. Just as neural networks in biological brains show coordinated activity patterns, galaxy networks might display similar coherence as they participate in universe-scale computational processes. If our universe exists within a black hole in a parent cosmos, then our scientific observations and theoretical understanding might be contributing to the information processing occurring at that higher level of organization. Our attempts to understand cosmic evolution could be part of the parent universe's effort to understand itself. Quantum mechanics tells us that the act of observation fundamentally changes the systems being observed, collapsing probability waves into definite states and determining the outcome of quantum measurements. But what if this observer effect operates on cosmic scales, with consciousness playing a fundamental role in determining the large-scale structure and evolution of the universe itself? If our universe exists within an infinite hierarchy of nested black hole cosmos, then conscious observers at each level might be actively participating in the creation and maintenance of reality at their scale. Our scientific observations and measurements could be helping to determine not just what we discover about the universe, but what properties the universe actually possesses. The anthropic principle suggests that we observe the universe to have properties compatible with our existence simply because we exist to observe them. But in a nested cosmic hierarchy, this relationship might be far more active and dynamic than previously imagined. Consider the implications for the ancient galaxies discovered by Webb. These objects formed when the universe was young and its properties were still stabilizing. The act of observing them now, billions of years after their formation, might be retroactively influencing their properties through quantum mechanical connections that operate across cosmic time. This would create a cosmic bootstrap paradox, where the universe develops properties that ensure the eventual emergence of observers capable of studying its early evolution. The observer effect would operate across space and time, creating self-consistent cosmic histories that support the development of consciousness. The rapid formation of complex structures in the early universe might reflect this observer-driven cosmic evolution. If consciousness at various levels of the cosmic hierarchy is actively participating in cosmic organization, then galaxy formation could proceed much more efficiently than purely physical processes would allow. Quantum entanglement might provide the mechanism for this cosmic scale observer effect. If particles and systems throughout the universe remain quantum mechanically connected across vast distances and timescales, then conscious observations anywhere in the cosmos could influence conditions everywhere else. The coordinated rotation of galaxies across cosmic distances might be evidence of this quantum entanglement operating on large scales. Rather than being independent systems, galaxies could be components of a vast quantum network, where measurement and observation at one location instantly affects conditions throughout the entire system. This perspective transforms scientific observation from passive data collection into active participation in cosmic creation. Every measurement we make, every theory we develop, every discovery we announce could be contributing to the ongoing process of universal self-organization. The nested universe hierarchy would amplify this effect across multiple levels of reality. Conscious observers in parent universes might be influencing the conditions in our cosmos, while our observations might be affecting the universes nested within the black holes in our local cosmic neighborhood. If our universe truly exists within a black hole in a larger parent cosmos, it raises a fascinating question about communication and information transfer between the different levels of the cosmic hierarchy. According to general relativity, nothing can escape from within a black hole's event horizon, including light, matter, and information. This would seem to make communication between nested universes impossible, trapping each cosmic level in complete isolation from its parents and its offspring. Yet the existence of organized structures and apparent fine-tuning in our universe suggests that information has somehow been transmitted from parent systems. The rapid formation of complex galaxies, the sophisticated chemistry of early star formation, and the coordinated patterns observed on cosmic scales all point to inherited organizational templates. The solution to this communication paradox might lie in the quantum mechanical nature of black hole formation and evolution. When a black hole forms through gravitational collapse, it does not instantly cut off all connection to the outside universe. Instead, the process of horizon formation and information encoding might allow for sophisticated transfer mechanisms operating through quantum entanglement. Hawking radiation provides one potential communication channel. As black holes slowly evaporate, they emit particles that might carry encoded information about the internal universe. From the perspective of the parent cosmos, this radiation could provide a slow but steady stream of data about the conditions within the nested universe. From our perspective within a black hole universe, we might be able to influence this communication channel through our collective activities as conscious observers. The development of advanced civilizations, the creation of complex technologies, and even the pursuit of scientific understanding might all contribute to information patterns that eventually influence the Hawking radiation emitted by our containing black hole. Consider the timescales involved. While communication through Hawking radiation would be extraordinarily slow from our internal perspective, It might operate efficiently from the viewpoint of the parent universe, where our entire cosmic history unfolds in a much shorter time frame due to relativistic effects. The coordinated galactic rotations observed across our universe might represent a form of cosmic-scale information encoding. If consciousness throughout our cosmos collectively organizes matter and energy in specific patterns, these patterns could be transmitted to the parent universe through quantum mechanical channels we do not yet understand. Another possibility involves the moment of black hole formation itself. The initial conditions that gave birth to our universe might have been encoded with sophisticated information templates from the parent cosmos. Rather than requiring ongoing communication, all the necessary organizational information could have been transmitted during the quantum bounce that created our expanding space-time. The rapid evolution of the early galaxies discovered by Webb might be direct evidence of this encoded information being expressed. As our universe expanded and cooled, the inherited organizational templates would begin to manifest as complex structures, forming much more quickly than purely random processes would allow. This suggests that while we cannot send messages back to our parent universe in any conventional sense, our collective development as a cosmic system might be generating information patterns that influence the properties of our containing black hole. In essence, our universe's evolution could be a form of slow, cosmic-scale communication. As we stand at the threshold of discoveries that could revolutionize our understanding of reality itself, we must confront questions that stretch the boundaries of science, philosophy, and human comprehension. If our universe exists within an infinite hierarchy of nested black hole cosmos, what does this mean for the concepts of beginning and ending, of uniqueness and significance, of isolation and connection? The very foundations of how we think about existence might need to be rebuilt from the ground up. The discovery of impossibly bright and sophisticated galaxies in our cosmic dawn forces us to question whether we have fundamentally misunderstood the nature of time, causality, and cosmic evolution. Perhaps what we interpret as rapid galaxy formation is actually the expression of organizational patterns that transcend our local space-time. Inherited from parent universes through quantum mechanical processes we can barely imagine, the question echoes across cosmic scales. From individual human curiosity to universal self-inquiry. If consciousness plays a fundamental role in cosmic organization, then our wondering about these mysteries might be contributing to the universe's own effort to understand its place in the larger hierarchy of reality. The ancient galaxies that prompted this investigation might be more than just astronomical objects. They could be cosmic fossils, preserving information about our universe's ancestry. Quantum archaeological artifacts that encode the history of how our reality inherited its properties from parent systems. Each discovery pushes us to confront the possibility that everything we thought we knew about cosmic uniqueness might be wrong. Rather than inhabiting a singular universe that began with the Big Bang and will end with heat death or collapse, we might be temporary participants in an infinite cycle of cosmic reproduction and evolution. The implications for human meaning and significance are profound. If our universe is one of countless nested realities, does this diminish our importance or enhance it? Are we cosmic accidents or essential components of universal self-organization? Do our lives and achievements matter only locally? Or do they contribute to information processing occurring on scales we cannot comprehend? The coordinated rotation of galaxies across cosmic distances might be evidence that we are already participating in forms of cosmic consciousness that operate beyond individual awareness. Our scientific discoveries, our technological achievements, and even our philosophical questioning might be contributing to patterns of cosmic organization that span multiple levels of the universal hierarchy. As astronomers continue to peer deeper into space and time with increasingly powerful instruments, They are simultaneously looking deeper into questions about the nature of reality itself. Each new ancient galaxy discovered represents not just another data point, but another piece of evidence that the universe is far stranger and more interconnected than our theories had suggested. The James Webb Space Telescope and its successors might be doing more than just studying distant objects. They might be facilitating communication between the different levels of cosmic organization, helping our universe to understand its place in the infinite hierarchy of nested realities. The ultimate questions are not just about what we will discover, but about how those discoveries will change our understanding of what it means to exist in a universe that might be far more alive, connected, and purposeful than we ever dared to imagine. Looking forward to the next decade of cosmic discovery, we find ourselves standing at the edge of what might be the greatest revolution in human understanding since we first realized that the Earth orbits the Sun. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will survey vast areas of the sky with unprecedented depth and precision, where Webb has opened windows into individual ancient galaxies. Roman will map the cosmic landscape on scales that could reveal the true extent of early universe complexity. Together, these space-based observatories will create the most comprehensive census of the cosmic dawn ever attempted. If current trends continue, they may discover thousands of bright, early galaxies, each one potentially forcing further revisions to our models of cosmic evolution. The statistical power of such a large sample could finally determine whether we are witnessing genuine departures from theoretical predictions or simply the extreme but expected outcomes of known physical processes. But perhaps more importantly, these observations might reveal patterns that point toward the nested cosmic hierarchy that some theories now suggest. If galaxies show coordinated properties across vast distances and cosmic time, it could provide the first direct evidence that our universe participates in organizational structures that transcend our local space-time. JWST itself appears poised to drive a series of great expansions of the cosmic frontier. Previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away. Each new discovery chips away at the assumption that our universe is an isolated system, revealing instead a cosmos that might be intimately connected to larger realities through quantum mechanical processes we are only beginning to understand. The search for population 3 stars continues, promising to reveal how the universe's first lights emerged from the primordial darkness. These cosmic pioneers could provide the missing link between the simple universe of the Big Bang and the complex chemistry required for planets and life. Advanced computer simulations running on the world's most powerful supercomputers are being designed to test whether the nested black hole universe theory can quantitatively explain the rapid formation of the early galaxies. If successful, these models could provide a new framework for understanding cosmic evolution that extends from the quantum scales to infinite hierarchies of nested realities. The implications reach far beyond astronomy. If our universe exists within a cosmic hierarchy, then every field of human knowledge, from physics to philosophy, from biology to consciousness studies, will need to be reconsidered in light of our interconnected cosmic status. Future generations might look back on this era as the moment when humanity first began to understand its true place in the infinite network of nested universes. The ancient galaxies that so surprised astronomers could be remembered as the first evidence that reality is far more vast, complex, and interconnected than anyone had dared to imagine. As we continue to decode the messages written in ancient starlight, we might be simultaneously learning to participate more consciously in the cosmic conversation that spans the multiple levels of reality. The universe is not just something we study, it might be something we help to create through the very act of understanding. We began this journey with a single point of light in the cosmic darkness. A galaxy so distant and ancient that it challenged everything we thought we knew about the universe's earliest chapters. Jade's GS Z14-0, shining across 13.5 billion years of space and time, became our gateway into mysteries that stretch from the quantum realm to infinite cosmic hierarchies. What started as an astronomical discovery evolved into questions about the very nature of reality itself. The galaxy that was supposed to be impossible turned out to be just the beginning. Its brightness without a central black hole. Its sophisticated chemistry appearing impossibly early. Its membership in a growing population of ancient cosmic giants all pointed toward a universe far more dynamic and interconnected than our theories had predicted. Each revelation built upon the last. Missing supermassive black holes led to questions about feedback mechanisms. Rapid chemical evolution challenged our understanding of stellar life cycles. The abundance of bright early galaxies suggested that dark matter and cosmic structure formation operated differently than we assume. But perhaps most profound of all was the growing evidence that galaxies across vast distances rotate in coordinated patterns, as if responding to some universal organizing principle that extends beyond local gravitational interactions. This cosmic choreography opened the door to the most radical possibility of all that our entire universe exists within a black hole in a larger parent cosmos. The implications cascade through every aspect of our understanding. If universes reproduce through black hole formation, then consciousness might play a fundamental role in cosmic evolution. The fine-tuning of physical constants could reflect an inheritance from successful parent universes. The rapid formation of early galaxies could express organizational templates encoded during our cosmic birth. We might inhabit not a unique, isolated universe, but one branch of an infinite tree of nested realities, each level contributing to a cosmic conversation that spans scales from the quantum to the infinite. Our scientific observations, our technological achievements, our very existence as conscious beings could be participating in information processing that operates across multiple levels of this vast hierarchy. The ancient galaxies discovered by Webb represent more than distant stellar nurseries. They are messengers from our cosmic dawn, carrying encoded information about our universe's ancestry and its place in the larger scheme of reality. Each photon that traveled billions of years to reach our telescopes might be part of a cosmic communication network that connects nested universes across infinite scales. As we stand on the threshold of even greater discoveries, we face a choice about how to interpret the evidence. We can cling to models that treat our universe as an isolated system, explaining away each anomaly with increasingly complex theoretical patches. Or we can embrace the possibility that reality is far stranger, more beautiful, and more interconnected than we ever imagined. The universe is not just something we study, it might be something we help to create through the very act of understanding. The endless frontier of cosmic discovery stretches ahead, promising revelations that could transform not just astronomy, but our entire conception of what it means to exist in a reality that may be infinite in its depth, complexity, and wonder. $13.8 billion years ago, everything we know exploded into existence from a point smaller than an atom. This has been our story, our cosmic genesis, the bedrock of our understanding. But the James Webb Space Telescope, an instrument of impossible precision, a $10 billion eye designed to gaze upon the universe's infancy, has just found galaxies that were already ancient when the universe was supposedly still a baby. We are seeing stars that formed heavy elements before the cosmos had time to cook them, massive black holes that grew impossibly fast, and structures so perfectly organized they shouldn't exist in a chaotic, young universe. The most powerful telescope ever built wasn't meant to destroy our origin story, but that's exactly what it's doing. Prepare yourselves. We begin. The James Webb Space Telescope cost $10 billion and took 30 years to build. This monumental effort, a testament to human curiosity and engineering, was not just about getting better space photos. Scientists had a specific, profound mission to prove that our story of cosmic creation was absolutely correct. For decades, we have told ourselves a simple, elegant tale. The Big Bang happened 13.8 billion years ago. Then came 400 million years of cosmic darkness. A silent, starless epoch while the universe cooled and gravity slowly, patiently, began to gather the primordial gas. Those first stars, when they finally ignited, were supposed to be simple, monstrously large, and made only of hydrogen and helium, the raw ingredients forged in the initial fireball. Galaxies, in this narrative, should have grown gradually, messily, over billions of years through countless collisions and mergers, like cities built slowly from scattered villages. This timeline was not just a theory. It was the foundation of modern cosmology. Every textbook, every documentary, every elegant equation that described our universe relied on this sequence of events. The standard model of cosmology, a framework of stunning predictive power, was built upon this assumption of a slow, hierarchical formation of structure. The James Webb Telescope was designed to be the ultimate witness to this process. Its unparalleled infrared vision could peer back through the expanding darkness, through the veil of cosmic dust, to the very edge of the cosmic dawn. It was meant to show us those first primitive stars struggling to ignite, to capture the faint, red-shifted light of the first fledgling galaxies as they flickered into existence. We expected to see a chaotic, violent universe slowly, painstakingly, organizing itself into the cosmos we know today. The telescope's 18 hexagonal mirrors, coated in a whisper-thin layer of gold, were polished to a perfection measured in atoms. Its instruments were calibrated to detect the faintest whispers of ancient light, photons that had traveled for more than 13 billion years to reach us. Scientists prepared to celebrate as the first observations confirmed what their powerful computer simulations had predicted for decades. The early universe should look young, disorganized, and exactly as messy as you would expect from a cosmos just learning how to exist. But when James Webb opened its golden eye and looked back toward the beginning of time, it did not find confirmation. It did not find the expected chaos. It did not find the primitive, stumbling galaxies of our theories. Instead, it discovered something that made astronomers question everything they thought they knew about cosmic history. The discoveries staring back at us from the cosmic dawn challenged not just the details of how galaxies formed, but the entire timeline of cosmic evolution. The implications reach far beyond astronomy. If our most fundamental story about reality is wrong, what does that mean for physics, philosophy, and our place in the universe? The telescope that was meant to prove our origin story might instead destroy it completely. 400 million years after the Big Bang, the universe should have been a cosmic wasteland. To put that into perspective, if the entire history of the cosmos was compressed into a single calendar year, we are looking at January 2nd. At that point, galaxies should be tiny, primitive collections of the very first stars, little more than glowing smudges in the endless dark. What James Webb found instead were massive, mature galaxies that looked as if they had been around for billions of years. These are not small collections of newborn stars struggling to survive. We are seeing galaxies with masses equivalent to 100 billion suns, perfectly organized into spiral arms and central bulges. Our own Milky Way galaxy took over 13 billion years to reach this level of development. Yet here are galaxies that somehow achieved this complexity when the universe was barely out of diapers. The numbers simply do not add up. Our most sophisticated computer simulations, which have successfully modeled the evolution of the universe for decades, show that galaxies this massive should take at least 2 billion years to form. Through the slow, arduous process of smaller galaxies merging together. But we are seeing them when the universe was only 400 million years old. It is like finding a fully grown oak tree in a garden that was planted yesterday. Dr. Ivo Labbé from Swinburne University described these discoveries as galaxy monsters that shouldn't exist. His team found galaxies so massive, they make up almost as much matter as all the stars that should exist in the entire observable universe at that time. The math simply does not work with our current understanding of cosmic evolution. It is a statistical impossibility, a cosmic contradiction written in the light of ancient stars. Even more puzzling is how organized these galaxies appear. The Big Bang Theory predicts that early galaxies should be chaotic and irregular, slowly forming structure through gravitational interactions over cosmic time. Instead, James Webb is showing us galaxies with clear spiral patterns, well-defined central bulges, and organized star formation regions. These are features that should take billions of years of quiet, stable evolution to develop. This discovery is forcing astronomers to confront an uncomfortable possibility. Either our understanding of how fast galaxies can form is completely wrong, or our timeline of cosmic history needs a major revision. Some scientists are beginning to whisper about alternative theories that could explain these observations. Theories that were once dismissed as fringe ideas. But accepting those alternatives means abandoning much of what we thought we knew about the universe. The implications stretch beyond just galaxy formation. If massive, organized galaxies existed this early, they would have profoundly influenced the entire structure of cosmic evolution. The gravitational effects of these monster galaxies should have left traces throughout the universe that we simply do not see in other observations. Yet, the evidence keeps mounting that these impossible galaxies are absolutely real. In the beginning, the universe knew only 3 elements: hydrogen, helium, and tiny, almost negligible traces of lithium. Every other element in the periodic table, the building blocks of planets, of life, of you, had to be forged inside the nuclear furnaces of stars and scattered through space when those stars died. This process of cosmic alchemy takes time, billions of years of it. Yet, James Webb is finding heavy elements in galaxies that formed when the cosmos was still a cosmic infant, a time when such complexity should have been impossible. Picture a star as a cosmic kitchen. It starts with the simplest ingredients, hydrogen and helium, and slowly cooks them into heavier elements through the intense pressure and heat of nuclear fusion. Carbon, oxygen, silicon, iron, all these elements require multiple generations of stars to create and distribute. The very first stars, the primordial giants, had to live their entire, brilliant, violent lives, explode as supernovae, and seed the surrounding space with these newly forged heavy elements. Only then could the next generation of stars form, incorporating those elements into their own structure and into the planets that would orbit them. This stellar cooking process is like a cosmic assembly line that cannot be rushed. The most massive stars burn through their fuel quickly and explode within a few million years. But even this fastest of cosmic assembly lines needs hundreds of millions of years to produce significant amounts of heavy elements. The universe at 400 million years old simply had not had enough time for this process to work. Yet, spectroscopic analysis of these early galaxies, a technique that breaks light down into its constituent colors to reveal its chemical composition, shows clear signatures of oxygen, carbon, and even heavier elements like silicon and magnesium. The concentrations are not trace amounts that might be explained by a few unusually fast-burning stars. We are seeing metal abundances that suggest multiple generations of star formation and death had already occurred. A level of chemical enrichment that rivals much younger, more evolved systems. Dr. Emma Curtis Lake, who led some of these early spectroscopic observations, described finding galaxies with metallicities that were simply staggering. The spectral lines, the dark bands in the rainbow of starlight that correspond to specific elements, do not lie. These galaxies contain elements that should not exist in such quantities for billions more years of cosmic evolution. This discovery creates a cascade of problems for our cosmic timeline. If heavy elements existed this early, then planet formation could have begun much sooner than predicted. Rocky planets like Earth, which require these heavier elements to form, could have been a common feature of the very early universe. The implications for when and where life might have first appeared in the universe become staggering. Suddenly, the timeline for biology is pushed back billions of years into an era we once thought was barren and inhospitable. Some astronomers are proposing that the very first stars, the population 3 stars, might have been much more massive than we thought, burning through their lives and creating heavy elements at unprecedented rates. Others suggest that star formation itself might work differently in the early universe than it does today, with different efficiencies and different outcomes. But both of these explanations require us to revise fundamental assumptions about stellar physics. Assumptions that have been tested and confirmed for decades. The elements James Webb found should not exist yet, but they are there, written in the light of ancient galaxies, challenging everything we thought we knew about cosmic chemistry. What we discovered next makes the heavy element problem look simple by comparison. Imagine trying to build a skyscraper during an earthquake while blindfolded. That is what galaxy formation should have looked like in the early universe. The cosmos was violent, chaotic, and filled with dark matter and gas crashing together in random collisions. Galaxies should have grown slowly and messily through countless mergers over billions of years. What James Webb found instead were galaxies that looked as if they had been designed by a cosmic architect. The Hubble Space Telescope had already shown us that distant galaxies appear more irregular and chaotic than nearby ones. This made perfect sense. We were looking back in time to see galaxies in their awkward teenage years, still growing and organizing themselves. James Webb was supposed to push even further back, to see cosmic toddlers stumbling around in the dark. Instead, we found galaxies with clear spiral arms, organized central bulges, and structured star formation patterns. These features require delicate gravitational balance and billions of years of quiet, stable evolution to develop. In our own cosmic neighborhood, only the most mature, undisturbed galaxies display such perfect organization. Yet here they were, in the cosmic dawn, looking impossibly sophisticated. Dr. Stephen Finkelstein from the University of Texas described these discoveries as finding adult galaxies in a cosmic nursery. The level of organization defies everything we know about hierarchical structure formation. The theory that predicts small objects merge to form larger ones over cosmic time. These galaxies appear to have skipped their messy childhood entirely, emerging fully formed from the chaos of the early universe. The smooth, thin disk structures are particularly puzzling. In today's universe, galaxy disks form through a complex process where gas slowly settles into stable, rotating patterns over hundreds of millions of years. Early in cosmic history, frequent mergers and chaotic gravitational conditions should prevent such delicate structures from forming or surviving. Yet, James Webb is showing us pristine spiral patterns that look as if they have never been disturbed, as if they have been spinning peacefully for eons. Even more mysterious are the central supermassive black holes that seem to be perfectly coordinated with their surrounding galaxies. In the modern universe, we observe tight correlations between the mass of a galaxy's central black hole and the properties of its host galaxy. This relationship takes billions of years to establish through a complex dance of feedback between star formation and black hole growth. Finding such coordination in young galaxies suggests processes we do not understand, a form of co-evolution that happens almost instantaneously. The implications of this discovery challenge the entire concept of cosmic evolution. If galaxies can organize themselves this quickly, then our understanding of how structure forms in the universe needs a complete overhaul. It suggests that there is a hidden organizing principle at work, a force or a mechanism that we have not accounted for in our models. The smooth, organized galaxies James Webb discovered should not exist for billions more years, but their perfect spiral arms are just spinning us toward an even stranger discovery about rotation speeds that appear to break the laws of physics. Galaxies rotate like cosmic hurricanes, vast, swirling systems of stars, gas, and dust held together by the gravitational embrace of dark matter halos that surround them like invisible cocoons. The faster a galaxy spins, the more mass it needs to prevent itself from flying apart. This fundamental relationship between rotation speed and mass is one of the most reliable and well-tested rules in astronomy. But James Webb found ancient galaxies spinning so fast they should have torn themselves to pieces billions of years ago. When astronomers measure how fast stars move in the disks of distant galaxies, they can calculate exactly how much total mass the galaxy contains. It is a simple application of physics, like watching cars on a circular racetrack. The faster they go without flying off the track, the steeper the banking of the road must be. In galaxies, that banking is provided by gravitational mass, mostly in the form of dark matter. The problem is that these early galaxies are rotating at speeds that require dark matter halos much more massive than anything our computer simulations of structure formation can produce. Some of these ancient galaxies are spinning at 300 kilometers per second, when they should be limited to perhaps 150. That is like finding a motorcycle taking a tight turn at twice the speed that should send it skidding into the wall. Dr. Claude-André Fauché-Giguère from Northwestern University has been studying these rotation curves and describes them as impossible under current models of galaxy formation. The dark matter halos required to stabilize such rapid rotation would be so massive that they should dominate the entire region of space around them. Yet, we do not see evidence for such monster halos in the structure of the cosmic web. Even stranger is how quickly these rapid rotation patterns must have established themselves. In today's universe, galaxy disks build up their rotation gradually as gas settles into stable orbits over hundreds of millions of years. But these ancient galaxies appear to have reached their maximum spin almost immediately after forming. It is like finding a figure skater already in a perfect, high-speed pirouette the moment they step onto the ice. The physics becomes even more problematic when you consider the conservation of angular momentum. As galaxies form from collapsing clouds of gas, they should spin up gradually as they shrink, just like a figure skater pulling in their arms. But the rotation speeds James Webb measured suggest these galaxies started with far more angular momentum than the cosmic web should have been able to provide. The initial conditions of the universe simply did not contain enough rotational energy to explain these observations. Some theorists are proposing exotic solutions, involving modified theories of gravity or alternative dark matter models that could provide the extra gravitational pull needed. Others suggest that early galaxy formation might involve processes we have never considered, like the transfer of angular momentum through cosmic magnetic fields. But every explanation requires abandoning well-tested physics or accepting that the early universe operated under a completely different set of rules. These impossibly fast-spinning galaxies are rotating us toward an even more disturbing discovery about collisions that happen before galaxies should have even had time to meet. Galaxy mergers are cosmic train wrecks that unfold over hundreds of millions of years. When two galaxies collide, their gravitational dance creates tidal tails, stellar streams, and distorted structures that astronomers can recognize, like forensic evidence at a crime scene. James Webb found this evidence in galaxies that formed when the universe was so young that such collisions should not have been possible yet. The timeline problem here is severe. According to our models, the first galaxies were tiny, isolated islands of stars scattered across vast distances of empty space. They were like cosmic hermits, too far apart and too small to interact with each other in any significant way. Major galaxy mergers, the kind that dramatically reshape galaxies, should have waited until the universe was at least 1 billion years old, when cosmic structures had grown large enough and close enough to gravitationally influence each other. Yet, James Webb is showing us clear merger signatures in galaxies from just 400 million years after the Big Bang. We are seeing tidal streams of stars being pulled away from galactic cores, double nuclei that indicate recent collisions, and asymmetric, distorted structures that can only result from gravitational encounters between massive objects. Dr. Jehan Kartaltepe from the Rochester Institute of Technology has been analyzing these early merger signatures and describes them as finding car crashes in a world where cars have not been invented yet. The morphological features are unmistakable. These galaxies have definitely collided with other massive systems, but the cosmic timeline says such collisions should be impossible this early in universal history. The discovery gets even more puzzling when you consider the merger rates. In the local universe, major galaxy mergers are relatively rare events. A galaxy like the Milky Way might experience one significant merger every few billion years. But in these early observations, merger signatures appear in almost every massive galaxy James Webb examines. It is as if the young universe was experiencing a collision epidemic, a period of frantic, chaotic merging that our theories never predicted. Even more problematic is the scale of these ancient mergers. We are not seeing small galaxies absorbing tiny companions. These are major mergers between systems that are already massive and well-developed. The energy required to disrupt such large galaxies and then reorganize them into the structures we observe should take billions of years. Yet, we are seeing the aftermath when the universe was barely 500 million years old. The implications of this discovery cascade through our understanding of cosmic evolution. If major mergers were common this early, they would have triggered massive bursts of star formation and fed the central black holes at unprecedented rates. This should have left observable signatures throughout the universe, in the distribution of matter and the properties of the cosmic background radiation that we simply do not see. Some astronomers are beginning to question whether our fundamental timeline of structure formation is completely wrong. Maybe the universe organized itself much faster, much more violently, and much more efficiently than we ever imagined possible. But the evidence for impossible timing does not stop with galaxy collisions. Next, we discovered something even more fundamentally challenging about the cosmic microwave background itself. The cosmic microwave background, or CMB, is the universe's baby picture. It is a snapshot of what the cosmos looked like just 380,000 years after the Big Bang. A faint, ancient light that carries the imprint of the tiny density fluctuations that would eventually grow into galaxies, stars, and everything we see today. But James Webb's observations suggest that this baby picture might be telling us the wrong story about how the universe actually developed. The CMB shows us a universe that was remarkably smooth and uniform in its early days. The variations in density were incredibly small, just 1 part in 100,000. These tiny ripples in the cosmic fabric were the seeds that would slowly, over billions of years, grow through gravitational attraction into the vast, large-scale structures we observe today. Cosmologists have used sophisticated computer simulations to grow these seeds forward in time, predicting exactly what the universe should look like at any given epoch. These models are incredibly detailed, tracking how dark matter clumps together, how gas flows between galaxies, and how stars form within those galaxies. These simulations confidently predict that at the time James Webb is observing, galaxies should be small, irregular, and relatively rare. But that is not what we are seeing. The massive, organized galaxies that James Webb discovered require initial density fluctuations that were much larger than what the cosmic microwave background recorded. It is like finding full-grown trees in a field where the soil analysis says only grass seeds were planted. The numbers do not match. Dr. Rajendra Gupta from the University of Ottawa has been comparing James Webb observations with CMB predictions and describes the mismatch as fundamentally problematic. The early universe appears to have had far more structure-forming power than the baby picture suggests was possible. The discrepancy is not subtle. Some of the galaxies James Webb found are so massive that they require regions of space that were overdense by factors that the CMB says should not exist. The statistical probability of such massive galaxies forming from the observed initial conditions is essentially zero. We should not be seeing them, and yet we are. This creates a paradox that strikes at the heart of modern cosmology. Either our interpretation of the cosmic microwave background is wrong, or our understanding of how cosmic structures grow from initial fluctuations needs a complete revision. Both possibilities would require abandoning fundamental assumptions that have guided cosmology for half a century. Some theorists are exploring exotic solutions, involving things like primordial black holes that could have acted as seeds for early galaxy formation, or modified theories of gravity that could have accelerated the growth of structure. Others are beginning to suggest that the CMB might not be the pristine, untouched record of initial conditions we once thought it was. Perhaps later events in the universe's history have altered its properties in ways we do not yet understand. The mismatch between our cosmic baby picture and what James Webb actually found growing in the universe is pushing us toward an even more disturbing discovery about black holes that grew impossibly fast. Quasars are the universe's most powerful lighthouses. Brilliant, distant objects powered by supermassive black holes that consume matter at extraordinary rates and blast energy across billions of light years. These cosmic monsters contain millions, or even billions, of times the mass of our sun. But James Webb found fully grown quasars shining when the universe was so young that black holes should have barely begun their journey towards such enormous sizes. Building a supermassive black hole is like constructing a skyscraper, one grain of sand at a time. The process requires patience and a tremendous amount of raw material. Even under the most ideal conditions, black holes can only grow so fast because the very energy they release while feeding heats up and pushes away the matter they are trying to consume. This natural speed limit is a fundamental part of black hole physics. The physics is unforgiving. When matter falls into a black hole, it heats up and glows brightly in an accretion disk before disappearing forever. This intense radiation exerts an outward pressure, acting like a cosmic traffic cop that regulates how much material can approach the black hole at any given time. The maximum growth rate, known as the Eddington limit, means that even a black hole that starts with the mass of 1,000 suns would need over 1 billion years to reach the billion solar mass range. Yet, James Webb discovered quasars powered by billion solar mass black holes when the universe was only 600 million years old. These are not modest black holes still growing toward maturity. They are fully developed supermassive objects, already dominating their galactic environments and powering some of the brightest objects in the cosmos. Dr. Xiaohui Fan from the University of Arizona has been studying these early quasars and describes them as finding adult elephants in a nursery full of mice. The growth rates required to explain these observations exceed the theoretical limits by factors of 10 or more. Either our understanding of black hole physics is incomplete, or these black holes started out much larger than anything our models predict. The discovery becomes even more puzzling when you consider where these black holes came from originally. The very first black holes should have formed from the collapse of the first generation of stars. which themselves took tens of millions of years to form and evolve. This means the seed black holes that would eventually become supermassive should have started with masses equivalent to perhaps 100 suns at most. Getting from 100 solar masses to 1 billion solar masses in 600 million years, while respecting the Eddington limit, is mathematically impossible. It is like trying to drive from New York to Los Angeles in 1 hour while obeying the speed limit. Some theorists are proposing that the first black holes might have formed through completely different mechanisms, like the direct collapse of massive gas clouds, which could have created seed black holes with much larger initial masses. Others suggest that black hole growth in the early universe might not obey the same physical limits we observe today, perhaps through mergers or super Eddington accretion. But these impossibly massive black holes are not just growing. They are feeding star formation at rates that defy our understanding. Stars are born in cosmic nurseries called molecular clouds, where gravity slowly compresses gas and dust until nuclear fusion ignites. This process has natural speed limits built into the physics of how matter behaves under extreme conditions. But James Webb found galaxies forming stars at rates so fast they violate every theoretical maximum we have calculated for stellar birth. In today's universe, even the most active star-forming galaxies, known as starburst galaxies, convert only about 1% of their available gas into stars every million years. This efficiency limit exists because star formation is a messy, wasteful process. When massive stars form, they blow powerful stellar winds and eventually explode as supernovae, heating up and dispersing the surrounding gas. This stellar feedback acts like a cosmic thermostat, regulating how quickly new stars can form. The most extreme star-forming galaxies we observe today create about 1,000 new stars per year. This rate is already considered extraordinary and unsustainable. Galaxies forming stars. This quickly will exhaust their gas supplies within a few 100 million years. Yet, James Webb discovered early galaxies with star formation rates exceeding 10,000 stars per year, sustained over periods that should have been impossible. Dr. Pascal Oesch from the University of Geneva has been analyzing these stellar birth rates and describes them as finding cosmic factories running at 10 times their maximum rated capacity. The energy output from such intense star formation should heat up and expel all the remaining gas, shutting down further stellar birth almost immediately. Yet, these galaxies appear to maintain these extreme star formation rates for hundreds of millions of years. The physics becomes even more problematic when you consider the raw materials required. Forming 10,000 stars per year requires consuming gas at rates that would exhaust even the largest known reservoirs within a cosmic blink of an eye. These galaxies would need a constant resupply of fresh material from their surroundings. But the early universe was much less dense than today, making such massive gas flows unlikely. Even more puzzling is how these galaxies managed to retain their star-forming gas in the first place. The intense radiation from such rapid star formation should create powerful galactic winds that blow gas out of the galaxy entirely. We observe this process in local starbursts, where stellar feedback eventually quenches star formation. But these early galaxies seem to be immune to their own stellar violence, continuing to form stars at a furious pace. The discovery suggests that star formation in the early universe operated under a completely different set of rules than what we observe today. Maybe the primordial gas was denser and colder, allowing it to collapse more efficiently. Maybe the stellar feedback was less effective, or the entire process of stellar birth was fundamentally different when the cosmos was young. Some astronomers are proposing exotic mechanisms involving primordial gas with unusual properties or gravitational conditions that no longer exist in the modern universe. Others suggest that our understanding of stellar feedback and gas dynamics needs a major revision. But these impossible star formation rates are not happening in isolation. They are organizing themselves into structures that challenge our understanding of cosmic evolution itself. The early universe should have been a scene of cosmic chaos, a violent, turbulent place where matter crashed together randomly as gravity struggled to organize the aftermath of the Big Bang. Large-scale structure, the vast network of galaxies and voids that defines the modern cosmos, should have emerged slowly and messily over billions of years through countless random collisions and mergers. But James Webb found a level of cosmic organization that suggests the universe knew exactly what it was doing from the very beginning. Picture the cosmic web as a three-dimensional spider web stretching across billions of light years, with galaxies strung along filaments of dark matter like dewdrops on silk strands. This web structure is one of the most beautiful and organized features of the modern universe. Computer simulations show that it should take at least 1 billion years for such organized patterns to emerge from the smooth, uniform initial conditions after the Big Bang. Yet, James Webb is revealing hints of large-scale structure and organized galaxy distributions in the cosmic dawn. When the universe was only a few 100 million years old, we are seeing aligned galaxy clusters, coordinated star formation patterns across vast distances, and gravitational influences between objects that should still be isolated islands in space. Dr. Casey Papovich from Texas A&M University has been mapping these early large-scale structures and describes them as finding a completed jigsaw puzzle when you expected to see scattered pieces still looking for their places. The level of gravitational coordination between distant objects requires a cosmic web that developed far faster than our models predict. The organization appears at multiple scales simultaneously. Not only are individual galaxies more structured than we expected, but they are also organized into groups and clusters that should not have had time to form. The gravitational binding energy required to hold such systems together suggests they assembled much more quickly and efficiently than the theory of hierarchical structure formation allows. Even more mysterious is how these organized structures maintain their coherence across such vast distances. In the early universe, light had not had enough time to travel between widely separated regions, meaning they could not coordinate their behavior through any known physical mechanism. This is known as the horizon problem. Yet, we are seeing correlated properties, like star formation rates and galaxy orientations, across scales that should be causally disconnected. This cosmic organization problem strikes at the fundamental assumptions about how the universe evolved from smooth initial conditions to the structured cosmos we observe today. If large-scale structure formed this quickly, it suggests either that the initial conditions were not as smooth as we thought, or that there were processes at work that we do not understand. Some cosmologists are exploring ideas about cosmic phase transitions, primordial magnetic fields, or exotic forms of dark energy that could accelerate structure formation. Others are questioning whether the initial conditions after the Big Bang were as smooth and random as we have assumed. But this organized cosmic architecture is not just empty space. It is supporting planetary systems that seem to have formed impossibly early in cosmic history. Rocky planets like Earth require a cosmic recipe that takes billions of years to prepare. You need multiple generations of stars to forge heavy elements, supernova explosions to scatter those elements through space, and then the slow, patient process of gravitational accretion to gather dust and debris into solid worlds. But James Webb has found evidence of planetary systems in galaxies so young that the ingredients for rocky planets should not even exist yet. Planet formation is like cosmic cooking that cannot be rushed. The first stars contained only hydrogen and helium, the simplest elements forged in the Big Bang itself. Every heavier element, the carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, the iron in our blood had to be manufactured inside the cores of stars and distributed by their explosive deaths. This process of element production takes time, even after heavy elements become available. Building planets is a slow process, Tiny dust grains must stick together to form pebbles. Pebbles must clump into boulders. Boulders must accumulate into asteroids. And asteroids must collide to build planets over tens of millions of years. The entire sequence. From the death of the first stars to the formation of the first rocky planets, typically requires at least 1 billion years of cosmic evolution. Yet, spectroscopic analysis of some early galaxies shows absorption features that could indicate the presence of dust and, potentially, even planetary debris in systems that formed when the universe was less than 800 million years old. Dr. Kevin Heng from the University of Bern describes these observations as finding evidence of planetary construction in a cosmic era when the building materials should not even exist. The implications of this discovery cascade through our understanding of when and where life might have first appeared in the universe. If rocky planets could form this early, then the conditions necessary for biology might have existed billions of years sooner than we ever imagined. The universe could have been teeming with potentially habitable worlds when our own solar system was still just a distant dream, an unformed cloud of gas and dust. Even more intriguing are the hints of atmospheric absorption in some of these early systems. While we cannot yet definitively confirm the presence of planetary atmospheres in such distant and ancient objects, the spectral signatures suggest the existence of complex chemistry involving heavy elements, arranged in ways that look suspiciously like atmospheric processes. The discovery forces us to reconsider how quickly planetary systems can assemble and begin operating as complex chemical laboratories. Maybe the process of dust grain sticking was more efficient in the early universe, or gravitational processes worked faster in the denser environment of cosmic youth. Some astronomers are proposing that the first planetary systems might have formed through mechanisms we do not observe in the modern universe, perhaps involving primordial materials or gravitational conditions that no longer exist today. But these rapidly forming planetary systems are not just an isolated puzzle. They are challenging our understanding of the cosmic inflation theory itself. Cosmic inflation theory proposes that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, stretching space faster than the speed of light and smoothing out any initial irregularities. This inflation should have created a universe with very specific, predictable properties, smooth on large scales, with tiny, precisely characterized fluctuations that would slowly grow into cosmic structure over billions of years. But James Webb's discoveries suggest the universe might not have followed the inflationary script at all. Inflation theory makes testable predictions about what the early universe should look like. The density fluctuations that eventually became galaxies should have specific statistical properties, following patterns that reflect the quantum mechanical processes that created them during the inflationary epoch. These fluctuations should be small, nearly scale invariant, and distributed according to precise mathematical relationships. The problem is that the massive, organized structures that James Webb discovered require initial fluctuations that were much larger and more organized than inflation predicts. The theory suggests that regions of space dense enough to form the observed massive galaxies should be extraordinarily rare, so rare that we should not see any in the cosmic volumes that James Webb can observe. Dr. Paul Steinhardt from Princeton University, one of the original architects of inflation theory, who later became one of its most prominent critics, describes these observations as potentially fatal problems for the inflationary paradigm. The statistical properties of the early galaxies do not match what inflation theory predicts should emerge from quantum fluctuations during a period of exponential expansion. Even more problematic is the coherent organization of structure across vast scales. Inflation theory predicts that different regions of space should have evolved independently after the rapid expansion separated them beyond any possible causal connection. Yet, James Webb's observations hint at coordinated properties and structures across distances that should be completely independent, according to inflationary cosmology. This discovery forces cosmologists to confront uncomfortable questions about whether cosmic inflation actually occurred, or whether it worked differently than our models suggest. Alternative theories that never required inflation are gaining renewed attention as potential explanations for James Webb's observations. Some theorists are exploring bouncing universe models, where our cosmos emerged from the collapse and rebound of a previous universe, potentially preserving organizational information that inflation would have erased. Others are investigating modified gravity theories or exotic forms of dark energy that could create the observed structure without requiring an inflationary expansion. The implications of this reach far beyond cosmology and into the realm of fundamental physics. Inflation theory has been intimately connected with our theories of quantum gravity and the earliest moments of cosmic history. If inflation is wrong, it suggests that our understanding of physics at the most fundamental level needs a major revision. But as multiple independent observations point to the same problems, the evidence becomes impossible to ignore. Science advances through the accumulation of evidence, and isolated anomalies can often be explained away by measurement errors, statistical flukes, or an incomplete understanding of the data. But when multiple, independent observations, using different techniques, all point to the same fundamental problem, the scientific community must confront the possibility that the accepted theories are simply wrong. James Webb's discoveries represent exactly this kind of converging evidence crisis. The telescope did not find just one type of anomaly. It discovered massive galaxies where small ones should exist, heavy elements that formed too quickly, organized structures that should be chaotic, rotation speeds that violate physics, collision signatures that predate possible interactions, star formation rates that break theoretical limits, and planetary systems that assembled impossibly fast. Each of these discoveries, taken alone, might be dismissed as an outlier or a statistical fluke, but together, they paint a consistent and deeply troubling picture of a universe that does not follow our rules. Independent research teams, using different analysis methods and looking at different regions of the sky, have confirmed these findings repeatedly. Dr. Labbé's galaxy mass measurements have been verified by multiple groups using completely different techniques. The spectroscopic evidence for early heavy elements has been detected in several independent surveys. The impossible rotation speeds have been confirmed through both direct velocity measurements and gravitational lensing studies. Even more compelling is how these diverse anomalies all point in the same direction, toward a universe that organized itself much faster and more efficiently than the standard Big Bang theory predicts. The problems are not random, scattered inconsistencies that might be explained by minor theoretical adjustments. They form a coherent and systematic pattern, suggesting that our fundamental timeline of cosmic evolution is wrong. The statistical weight of this accumulated evidence is becoming overwhelming. When astronomers calculate the probability that all of these observations could be explained by a combination of measurement errors or rare statistical fluctuations, the numbers become vanishingly small. We are not looking at a series of unlucky coincidences. We are seeing systematic discrepancies that demand a profound explanation. This convergence of evidence is forcing theoretical physicists to abandon incremental modifications to existing theories and begin to consider revolutionary alternatives. Dr. Subir Sarkar from Oxford University describes the situation as a paradigm crisis, a term used in the philosophy of science to describe a moment when accumulated anomalies can no longer be accommodated within the existing theoretical framework. The process mirrors historical scientific revolutions, where multiple, independent observations eventually forced a complete theoretical overhaul, just as the discovery of stellar parallax, galactic redshifts, and the cosmic microwave background converged to establish the Big Bang theory in the first place. James Webb's discoveries might be converging to overthrow it. Scientific institutions are beginning to acknowledge that these discrepancies require serious theoretical attention rather than ad hoc explanations. Major funding agencies are directing resources toward alternative cosmological models that could explain James Webb's observations without violating fundamental physics. The accumulated weight of evidence is pushing theoretical physicists toward completely new models of cosmic evolution. Behind closed doors in physics departments around the world, theorists are working frantically to develop alternative cosmological models that could explain James Webb's impossible observations without breaking the known laws of physics. These are not minor adjustments to existing theories. They are revolutionary new frameworks that could replace the Big Bang theory entirely. The quiet urgency of this theoretical work reflects how seriously physicists are taking the mounting evidence crisis. Dr. Neil Turok from the Perimeter Institute has been developing cyclic cosmology models, where the universe undergoes infinite cycles of expansion and contraction, with each cycle preserving organizational information that could explain the rapid structure formation James Webb observed. These models suggest our universe might not have had a beginning at all, but rather emerged from the organized collapse of a previous cosmic cycle. Meanwhile, Dr. João Magejo from Imperial College London is exploring variable speed of light cosmologies, where the fundamental constants of physics, like the speed of light, were different in the early universe. If light traveled faster in cosmic youth, it could allow widely separated regions of space to coordinate their evolution, explaining the large-scale organization James Webb discovered without requiring impossible timescales. Modified gravity theorists like Dr. Sabine Hossenfelder are investigating whether gravitational physics itself works differently on cosmic scales or in extreme environments. If gravity was stronger or operated through additional dimensions in the early universe, structure formation could proceed much faster than general relativity predicts, naturally explaining the mature galaxies James Webb found. Even more radical are theories involving multiple universes or higher dimensional physics. Some models suggest our observable cosmos might be embedded in a larger multiverse structure, with matter and energy flowing between connected regions through mechanisms we do not yet understand. These scenarios could provide the additional organizational power needed to explain rapid cosmic evolution. Dr. Paul Frampton from the University of North Carolina has been exploring bouncing cosmologies, where dark energy cycles between expansion and contraction phases, creating periods of accelerated structure formation that could explain James Webb's observations. These models abandon the idea of a single Big Bang in favor of multiple cosmic epochs with different physical properties. The theoretical work is proceeding with unusual urgency because the observational evidence continues to mount faster than explanations can be developed. Each new James Webb discovery adds further constraints that eliminate more traditional explanations, forcing theorists toward increasingly exotic alternatives. What makes this theoretical revolution particularly significant is how it is happening across multiple sub-disciplines simultaneously. Cosmologists are revising their models of cosmic evolution. Particle physicists are questioning our understanding of fundamental constants. And astrophysicists are reconsidering the processes of stellar and galactic formation. The James Webb crisis is forcing a coordinated rethinking of physics itself. Some of the most promising new models involve what physicists call emergent gravity. The idea that gravitational attraction might not be a fundamental force, but rather an emergent property arising from more basic quantum mechanical processes. If gravity works differently than we thought, it could explain why cosmic structures form so much faster than our current theories predict. But these new theoretical frameworks are approaching a tipping point, where they might fundamentally change our understanding of time and space itself. Einstein's theory of relativity taught us that space and time are woven together into a single, unified fabric called space-time, which can be stretched, warped, and curved by the presence of matter and energy. This profound understanding has been tested countless times and forms the very foundation of modern cosmology. But James Webb's discoveries are forcing physicists to question whether space-time itself might work differently than we have assumed. especially in the extreme conditions of the early universe. The problem is not just that galaxies formed faster than expected. It is that they formed in ways that seem to violate the principle of causality itself. Structure formation requires information to travel between different regions of space so they can coordinate their gravitational behavior. But in the early universe, many of the organized structures James Webb discovered are separated by distances that light had not had time to cross, making such coordination impossible under our current understanding of space-time. Dr. Lee Smolin from the Perimeter Institute has been exploring theories where time itself might be an emergent property, rather than a fundamental aspect of reality. In these models, what we experience as the flow of time could be an approximate description that breaks down under the extreme conditions of the early universe. If time worked differently, it could allow for processes that seem impossible under our current physics. Even more radical are theories suggesting that space might have additional, hidden dimensions that were accessible in the universe's youth, but became curled up and hidden as the universe evolved. These extra-dimensional models could provide pathways for information and energy to travel faster than the speed of light in our familiar three-dimensional space, explaining the impossible coordination James Webb observed. Some physicists are even investigating whether the speed of light itself might not be a constant throughout cosmic history. If light traveled faster in the early universe, it would allow widely separated regions to communicate and coordinate their evolution, naturally explaining the large-scale organization that formed too quickly under our current physics. Dr. Carlo Rovelli from the French National Center for Scientific Research has developed loop quantum gravity theories, where space-time itself is quantized, made up of discrete, indivisible units rather than being a continuous fabric. In these models, the very fabric of space-time might behave in strange and unpredictable ways under the extreme conditions of the early universe, allowing for structure formation processes that are impossible in the smooth, continuous space-time of classical physics. The implications of these ideas reach far beyond cosmology and into the very nature of reality itself. If our understanding of time and space is fundamentally wrong, it affects everything from the foundations of quantum mechanics to the possibility of time travel. The James Webb discoveries might be showing us that the universe operates according to a deeper level of physics that we have not yet discovered. These space-time theories are all converging on a single, disturbing possibility that the Big Bang might not have been the beginning of everything after all. For nearly a century, the Big Bang has been more than just a scientific theory. It has been our culture's origin story, the ultimate answer to the profound question of where everything came from. But James Webb's discoveries are forcing us to confront the possibility that the Big Bang might not have been the beginning of everything, but rather just one event in a much larger, much older cosmic story that we are only now beginning to understand. The evidence is pointing toward a universe that was already organized and structured when the event we call the Big Bang occurred. The massive galaxies, the early heavy elements, and the coordinated large-scale structures that James Webb discovered all suggest that cosmic evolution did not start from a smooth, uniform, and simple beginning. Instead, they hint at a universe that inherited its organizational information from whatever came before. Dr. Anna Ijas from New York University has been developing models where the Big Bang emerges from the collapse and bounce of a previous universe. In these scenarios, the organized structures that James Webb observed could be the fossilized remnants of cosmic evolution that preceded our current phase of expansion. The universe might undergo infinite cycles of expansion, contraction, and rebirth, with each cycle preserving and building upon the information from the previous one. Even more revolutionary are theories suggesting that multiple universes might exist simultaneously, with matter and energy flowing between them through mechanisms we do not yet understand. If our observable cosmos is connected to a larger multiverse, it could explain where the organizational power for such rapid structure formation came from. It was simply borrowed from neighboring universes. Some physicists are exploring the possibility that the Big Bang was actually a phase transition rather than a creation event, just as water can transition from ice to liquid to vapor, while remaining the same fundamental substance. The universe might have transitioned from one physical state to another without actually beginning to exist. Dr. Abhay Ashtekar from Pennsylvania State University has developed loop quantum cosmology models where the Big Bang singularity is replaced by a big bounce, a transition from a contracting phase of cosmic evolution to our current expanding phase. In these models, the universe has no beginning and no end, but rather undergoes eternal cycles of expansion and contraction. The philosophical implications are staggering. If the Big Bang was not the beginning, then questions about what came before it become scientifically meaningful rather than just metaphysical speculation. The universe might be infinitely old, with our current expansion phase being just one chapter in an eternal story. This possibility challenges not just our cosmology, but our entire understanding of causation, existence, and the nature of reality itself. If the universe has always existed in some form, it changes how we think about everything, from the origins of the physical laws to the possibility of life having existed in previous cosmic cycles. The James Webb discoveries might be showing us that we are not the first chapter of cosmic evolution, but rather the latest chapter in an infinite book. The scientific revolution brewing in cosmology is not just about adjusting details or fine-tuning existing theories. James Webb's discoveries are approaching a critical threshold where the accumulated evidence might force the complete abandonment of our current cosmic origin story in favor of something entirely different. We are standing at the edge of a paradigm shift that could rival the Copernican revolution in its scope and its implications for human thought. The tipping point in science comes when anomalies can no longer be explained by modifying existing theories. In the history of science, this moment arrives when multiple, independent lines of evidence all converge on the same conclusion that the fundamental assumptions underlying the accepted theory are simply wrong. The James Webb discoveries are rapidly approaching this critical mass of contradictory evidence. Dr. Subir Sarkar from Oxford University describes the current situation as a crisis of epic proportions in cosmology. The standard model of cosmic evolution requires increasingly exotic and elaborate modifications to accommodate each new James Webb observation. Dark energy must be more complex. Dark matter must behave differently. Inflation must work in ways we never imagined. And stellar physics must operate under a completely different set of rules in the early universe. The mathematical contortions required to save the Big Bang theory are becoming so elaborate that many physicists are questioning whether it is time to abandon the theory entirely, rather than continue patching it with increasingly implausible modifications. It is reaching the point where the cure is becoming worse than the disease. Major scientific institutions are beginning to acknowledge the severity of the crisis. The European Space Agency has approved funding for missions specifically designed to test alternative cosmological models. The National Science Foundation in the United States has created new funding categories for research into non-standard cosmologies. These institutional responses reflect a growing recognition that the James Webb discoveries represent more than just interesting anomalies. The convergence of evidence is accelerating. Every few months, new James Webb observations add to the pile of inexplicable data. The statistical probability that all these anomalies could be explained by measurement errors or theoretical oversights is approaching zero. The universe that James Webb is revealing simply does not match the universe that our theories predict. Historical precedent suggests that we are approaching the moment when the scientific community will be forced to choose between increasingly implausible explanations for the existing theory and revolutionary new models that naturally explain the observations. The geocentric Ptolemaic system of planetary motion required increasingly complex epicycles to match observations, until Copernicus proposed that the Sun, not the Earth, was the center of the solar system. We might be witnessing a similar moment in cosmology, The Big Bang Theory is requiring increasingly complex modifications to match James Webb's observations. Alternative theories that seemed radical just a few years ago are beginning to look like natural and elegant explanations for what we are actually seeing. The next few years of James Webb observations will likely determine whether we are looking at the end of the Big Bang era in cosmology and the beginning of something completely new. The story of how the universe began is not just a scientific theory, it is the foundation of how we understand our place in existence itself. If James Webb's discoveries force us to abandon the Big Bang theory and embrace a completely different cosmic origin story, the implications will cascade through every aspect of human knowledge, from philosophy and religion to our most basic sense of meaning and purpose. Throughout history, changes in our cosmic story have triggered profound shifts in human consciousness. When Copernicus showed that the Earth was not the center of the universe, it did not just change astronomy, it revolutionized philosophy, religion, and humanity's sense of its own importance. When Darwin revealed that life evolved through natural selection rather than being specially created, it transformed not just biology, but our entire understanding of what it means to be human. The James Webb revolution promises to be even more fundamental. If the universe has always existed in some form, with no ultimate beginning, it challenges our most basic assumptions about causation, creation, and the nature of existence itself. The questions that have driven human inquiry for millennia. Why is there something rather than nothing? What came before the beginning? What is our cosmic purpose would need to be completely reframed. Dr. Carlo Rovelli, from the French National Center for Scientific Research, argues that major scientific revolutions always force us to reconstruct our understanding of reality from the ground up. The James Webb discoveries are not just challenging cosmology, they are challenging the conceptual frameworks we use to understand existence itself. If the universe operates according to a level of physics we have not yet discovered, with time and space working differently than we have assumed, it opens up possibilities we can barely imagine. Maybe consciousness plays a fundamental role in cosmic evolution. Maybe information is more fundamental than matter and energy. Maybe the universe is stranger and more wonderful than our current theories even allow us to suggest. The implications extend to the possibility of life itself. If rocky planets and complex chemistry emerged billions of years earlier than we previously thought, the universe might have been teeming with life when our own solar system was still just a distant possibility. We might not be among the first intelligent beings to contemplate the cosmos, but rather the latest in an unimaginably long chain of cosmic evolution. Even our understanding of death and time could be transformed. If the universe undergoes eternal cycles of expansion and contraction, with information being preserved across these cosmic phases, it raises profound questions about whether anything is ever truly lost. The James Webb discoveries might be showing us a universe where existence itself is eternal and indestructible. The psychological adjustment to a completely new cosmic story will be challenging. Humans have always needed origin stories to provide meaning and context for their lives. The Big Bang Theory, for all its scientific precision, also served as a modern creation myth that helped people understand their place in the cosmos. But perhaps the most profound implication is that the James Webb discoveries remind us of how much we still do not know. The universe continues to surprise us, revealing new mysteries just when we thought we had everything figured out. The greatest discovery might not be any specific new theory, but rather the humbling recognition that the cosmos is far stranger, more complex, and more wonderful than we ever imagined. The James Webb Space Telescope was built to confirm our understanding of cosmic origins. Instead, it might be showing us that the greatest adventures in understanding are still ahead of us, waiting to be discovered in the infinite mystery of existence itself. We set out to prove our cosmic origin story with the most powerful telescope ever built, expecting to find confirmation of everything we thought we knew about the universe. Instead, James Webb showed us galaxies that should not exist, stars that formed too quickly, and structures too organized for a universe in its youth. The telescope that was meant to be the ultimate witness to the Big Bang might instead be writing its obituary. The evidence is overwhelming and undeniable. Massive galaxies in the cosmic infancy, heavy elements that formed impossibly fast, rotation speeds that break the laws of physics, collision signatures that predate possible interactions, star formation rates beyond all theoretical limits, and planetary systems that assembled before their ingredients should have even existed. Each of these discoveries, taken alone, might be explained away, but together, they paint a consistent and damning picture of a universe that refuses to follow our rules. This is not just a crisis in cosmology. It is a revolution in our understanding of reality itself. The accumulated weight of James Webb's observations is forcing physicists to question not just when the universe began, but whether it had a beginning at all. We might be witnessing the end of the Big Bang era and the birth of a completely new cosmic story. The implications cascade through every aspect of human knowledge. If time and space work differently than we have assumed, if the universe has always existed in some form, if cosmic evolution operates according to a level of physics we have not yet discovered, then everything we thought we knew about existence needs to be reconsidered. The questions that have driven human inquiry for millennia must be completely reframed. But perhaps the most profound discovery is how much mystery remains. The universe continues to surprise us, revealing new wonders just when we thought we had everything figured out. The James Webb observations remind us that the cosmos is far stranger, more complex, and more wonderful than our theories suggest. The greatest scientific revolutions in history began with observations that did not fit the existing theories. Copernicus, Darwin, Einstein all started with pieces of evidence that forced humanity to reconstruct its understanding of reality from the ground up. The James Webb discoveries might represent the beginning of a similar revolution, one that will transform not just cosmology, but our entire conception of existence itself. We stand at the threshold of a new cosmic story, one that might reveal the universe to be eternal, infinite, and far more mysterious than we ever imagined. The telescope that was built to confirm our origin story might instead be opening the first chapter of an entirely new book of cosmic understanding. The greatest adventures in discovery are not behind us. They are waiting to be written in the light of ancient galaxies that refuse to follow our rules, in the spin of impossible stars, and in the organization of a universe that seems to have known exactly what it was doing from the very beginning. The story of how the universe came to be is not ending. It is just beginning to be told.
The darkness was not absence. It was the pause before a breath, the moment before a thought becomes language. There were no stars, no time, no rhythm, only the absolute stillness of a silence that did not yet know it was silent. In that silence, something stirred. Not a spark, not even motion, just the possibility of becoming. And then, it began. Not with an explosion or a flash, but with the unraveling of non-existence into form. Space did not stretch into something that had once been empty. It was space itself that unfolded like a newborn wing, carrying with it time, temperature, and the tension of expansion. The first breath of being. In that instant, the universe bloomed not into stars, not yet, but into raw energy so dense it could not distinguish itself from itself. It surged outward faster than any particle could chase, a rush not of movement through space, but of space itself expanding. This was not like a fireball rising in the sky, but like an idea filling a mind that had only just been invented. Everything we know, atoms, stars, the breath you just took, was still locked in potential. For the first 10 millionth of a trillionth of a second, there were no particles, only a sea of radiant tension, a field of quantum flickers where nothing held shape. Time ticked in intervals so small that the word interval loses meaning. But cooling brings structure, and as the young cosmos released its initial fever, it allowed the formation of the first fragments of form. Quarks jittered into existence, so restless they refused to be alone. Gluons danced between them, insisting on bonds that gave birth to protons and neutrons. This dance was violent and brief, and only in the narrowest window of temperature and timing could these particles hold hands long enough to matter. The air, though, there was no air thickened with interactions. From pure energy, from light itself, mass had begun to coalesce. These were not yet atoms. Electrons still soared too fast to be tethered, and light could not travel freely. The newborn universe was a clouded womb of charged particles, scattering photons like marbles across glass. If you had eyes in that fog, you would have seen nothing. If you had ears, you would have heard silence broken by the hiss of chaos. And yet something was beginning to change. Within those first few minutes, the universe cooled just enough for protons and neutrons to fuse. They created the simplest nuclei, hydrogen first, then helium, and the rare hint of lithium. This period, brief and irrevocable, stitched together the elemental thread from which all later complexity would be spun. The numbers, strange as they seem, still echo through the cosmos: 75% hydrogen, 25% helium, and traces so faint they barely whisper. These ratios were set not in stars, but in that primordial moment, when there were still no stars to shape or shine. The light that tried to escape could not. Electrons and photons collided endlessly, bouncing through a universe still too hot for stillness. But behind the fog, the orchestra was tuning. With every passing heartbeat of cosmic time, the temperature dropped, and the first outlines of permanence began to trace themselves into being. Soon, the forces that govern everything would begin to separate, each peeling away from the original unity that had once bound them. Gravity, the weak and strong nuclear forces. Electromagnetism, once indistinguishable, would take on distinct roles. Their divergence was not a collapse, but a kind of crystallization, like water freezing into geometric symmetry, defining shape and direction where none had existed before. And so, from a nothing that was not truly nothing, a universe took its first steps into becoming, not with thunder or light, but with quiet laws unfolding in a darkness too dense to allow vision, a darkness not of absence, but of infinite potential yet unshaped. 1,000,000 years might pass without a single sound if there is nothing to carry it. After the first 380,000 years, silence in the early universe was no longer just a metaphor. It was a physical reality. As the newborn cosmos exhaled its heat into ever-expanding space, its temperature fell below a threshold that allowed electrons, for the first time, to slow and settle into orbit around the nuclei that had formed long before them. The particles that had wandered like restless ghosts finally found their place, and from this delicate embrace, the first atoms emerged. That union did not merely create matter, it changed the very transparency of the universe. Light, once trapped in an endless ricochet of collisions, was suddenly released, and with it came a new kind of clarity. Photons poured into the openness, stretching and fading as space expanded, leaving behind a faint glow, a whisper of the infant cosmos that still surrounds us in all directions. This is the cosmic microwave background, the earliest light we can detect, not because it was the first, but because it was the first allowed to travel freely. Yet even with the birth of atoms and the liberation of light, the universe had no stars. The sky was dark, though not empty. It was filled with potential, with hydrogen and helium clouds drifting through space like scattered ash, remnants of a fire whose embers had not yet reignited. This was the age of silence in a different form the time cosmologists call the Dark Ages, not because there was no activity, but because the light had not yet returned in new forms. Invisible threads of gravity began to tug gently at the vast sheets of gas. In some regions, matter clumped just slightly more densely than in others, and these tiny differences grew steadily over hundreds of millions of years. The universe was laying down a kind of scaffolding, invisible and immense, an intricate web upon which future galaxies would hang like dewdrops. There were no galaxies yet, no suns, no planets or moons, just darkness, and the slow tightening of gravity's fingers. Eventually, in these dense knots, clouds began to contract. As they collapsed under their own weight, the temperature at their centers began to rise. Pressure mounted, and then, quietly and invisibly, fusion was born. The first stars lit up like flares in the abyss. They were nothing like the stars we know. Massive, short-lived, and unpolluted by the complex chemistry that defines our solar system. These were elemental furnaces, raw and primitive, composed almost entirely of hydrogen and helium. They lived fast and died violently, burning through their fuel in only a few million years. Their lives were short, but their deaths rewrote the cosmos. In their cores, under unimaginable heat, they had forged new elements: carbon, nitrogen, oxygen, pieces of a puzzle that had never before existed. When they exploded as supernovae, they hurled these creations into space, seeding the vast darkness with materials that would one day form planets, oceans, blood, and thought. The violence of these first explosions did not end in destruction. Their shockwaves compressed nearby gas clouds, triggering the birth of new stars, each formed from matter more complex than the last. A lineage had begun, a cosmic ancestry of stars, each generation inheriting a richer chemical legacy than the one before. But that was still in the future. In the universe's early years, every new light that flared to life pushed back the darkness just a little more. As ultraviolet radiation from these ancient stars poured into space, it began to tear apart the hydrogen atoms that filled the void. Photons stripped electrons from protons, reionizing the universe, and in doing so, ending the cosmic dark ages. The universe, once dim and unformed, now shimmered with a growing lattice of starlight. Galaxies began to coalesce at the nodes of the cosmic web, spinning into spiral arms and elliptical clouds, dancing to the rhythm of gravity. What had begun as chaos had turned toward order, not because it was designed, but because the rules were written in the fabric of space and time. Still, nothing about this unfolding was predictable in the way we often imagine inevitability. If quantum fluctuations had danced just slightly differently, the stars we know, the planets we stand on, might never have formed. Our entire cosmic structure balances on the edge of these ancient uncertainties, ripples in the vacuum that inflation magnified into the framework of everything. A strange irony persists: the cold silence after the Big Bang had to last for hundreds of millions of years before heat and light could return in meaningful form. Before the sun could rise, the universe had to rest. Before atoms could bind into molecules, the space between them had to cool. In this long pause, the stage was set, not by force, but by the absence of it. And then, one star became many. One cloud gave rise to a cluster. One explosion echoed into dozens. And from this silent beginning, the sky learned to sing. The quiet chorus of stars, once scattered and few, began to crescendo into constellations of complexity. Galaxies, spun into being by the invisible architecture of dark matter, turned slowly in space, their spiraling arms cradling billions of suns. These spirals were not perfect or pristine. They grew through violence. Gravity, indifferent to the scale of suffering, pulled smaller galaxies into the bellies of larger ones. The sky itself became a history of collisions. Each encounter was both destruction and genesis. When galaxies merged, stars were flung into elliptical halos, gas clouds compressed into newborn clusters, and supermassive black holes at their centers edged closer, eventually coalescing in silence too deep for sound. These central black holes, once just strange theoretical outcomes of general relativity, became cosmic engines. As matter spiraled toward their event horizons, it heated and screamed in high-energy light, illuminating the cores of galaxies and powering quasars that shone more brightly than entire clusters. But even their brilliance could not overcome the strange truth that most of what exists does not shine. As telescopes reached further into the cosmic past, as instruments strained to measure gravitational pull versus visible mass, astronomers began to suspect an absence so massive it reshaped their understanding of presence. Stars spun in galactic disks faster than gravity from visible matter should allow. Something unseen was holding them together. Dark matter. Not because it is black or even shadowed, but because it neither absorbs nor emits light. It is invisible to every wavelength we know, detectable only by its gravity. It may outnumber normal matter by a factor of 5. It surrounds galaxies like a cloak, and forms the very scaffolding upon which all visible structure is hung. It does not collide, does not clump into planets or stars, does not burn. And yet it is what allows the night sky to exist at all. Then there is the deeper silence, still dark energy. Unlike dark matter, which pulls, dark energy pushes. It is not a force we can localize or isolate. It permeates space itself, a kind of pressure written into the void. In the late 20th century, astronomers measuring the light of distant supernovae discovered something that stunned the field. The expansion of the universe was not slowing as expected, but accelerating. This defied centuries of assumptions. Gravity, even on cosmic scales, was expected to act as a brake, gradually slowing the outward rush born from the Big Bang. Instead, the galaxies are speeding away from one another faster with time, carried by a space that seems to stretch more eagerly the more it expands. No one fully knows what dark energy is. Some think it is the cosmological constant, a fudge factor Einstein once inserted into his equations and later called his greatest mistake. Others imagine it as a quantum field, fluctuating with the fabric of space-time. And still others wonder whether it is a sign that our understanding of gravity is incomplete at the grandest scales. Whatever its nature, its implications are clear. The fate of the universe may not be a gentle coasting or a collapsing return. It may be an eternal, accelerating separation. In time, galaxies beyond our local group will speed so far and so fast that their light will never reach us again. The night sky, once full of stars, will become a smaller and smaller window into a shrinking past. Even light itself is not eternal. Photons from the cosmic microwave background continue to stretch, their energy fading with every heartbeat of expansion. One day, even that background glow may fall below detection, and the record of the universe's birth will vanish from view. This accelerating drift is not a tearing or breaking. It is the absence of grip, the emptiness of distance growing too fast to be bridged. And though the galaxies still dance, though stars still burn and die, there is a slow inevitability building in the background, the quiet extinguishing of connection. We live in a golden age not because our time is special in its content, but because we can see. We are early enough that the echoes of the beginning still wash over us. We can study the birth of time, map the expansion of space, and trace the fingerprints of invisible forces. But this window will not stay open. The past is not only behind us, it is also fading. And so the stars remain, for now, as reminders of a universe that once burst from nothing into brilliance, that once seeded its silence with the raw ingredients of life. Their light crosses unimaginable distances to find us. But in the far future, the silence will grow again, not from absence, but from distance untraversed, light undelivered, and stories untold. A planet coalesced from dust and ash in the outer spirals of a medium-sized galaxy. Third from a yellow star, it spun without language for billions of years, collecting the minerals and elements flung outward by generations of dead stars. Carbon, forged in ancient cores. Iron, birthed in supernovae. Oxygen and nitrogen, drifting freely in interstellar clouds before gravity sculpted them into air and ocean. There was nothing inevitable about the shape it took. Seas did not have to form. Atmosphere did not have to hold. Life did not have to arise. But chemical restlessness danced across clay and hydrothermal vent. And eventually, patterns emerged that could make copies of themselves. Simple at first, then layered, folded, armored, motile. Complexity rose, not in a straight climb, but in fits of catastrophe and reinvention. Through extinction and mutation, intelligence emerged, not as a trait, but as an accident of survival. On this single planet, in this modest corner of the cosmos, matter began to wonder about itself. Eyes turned upward not just in fear or navigation, but in curiosity. Something in the minds shaped by starlight began to ask what stars were. That question took millennia to articulate, and longer still to answer. Eventually, tools of glass and steel were pointed at the sky. Telescopes extended the eye. Accelerators cracked apart the smallest pieces of the known. Mathematics began to uncover rhythms hidden beneath the visible, and slowly, the universe started to explain itself through the minds it had unwittingly produced. But in that very effort, noble, wondrous, there came a growing awareness of limits. The more we learned, the more fragile the known became. The constants of nature were not merely numbers. They were balances on a razor's edge, the strength of gravity, the charge of the electron, the density of dark energy, each tuned within narrow margins that permit galaxies, stars, chemistry, breath. If gravity were slightly stronger, stars would burn out in moments, collapsing into black holes before life could find a foothold. If it were slightly weaker, matter might never have clumped, leaving a universe of eternal fog. The ratio of forces, the timing of phase transitions, the presence of matter at all, none of it demanded by logic. All of it balanced so precariously that some began to wonder whether such precision could be coincidence. From that doubt arose the anthropic principle, not as theology, but as contemplation. Perhaps the universe appears tuned for life, because only a tuned universe allows observers to arise at all. There could be many universes, infinite or near so, each with different laws. Ours would then be unremarkable, just one bubble in a sea of failure and silence, where finally, the music played long enough to listen to itself. This idea leads to the multiverse, not a fantasy, but a theoretical consequence of inflation, quantum mechanics, or string theory, depending on the path taken. In some versions, new universes bud off from quantum fluctuations like dew on a spider's web, each isolated and unreachable. In others, our own universe exists on a brain floating in a higher dimensional space, colliding now and then with others like it, triggering new cosmic births. None of these are proven, but all are consistent with the mathematics that describe the world we can test. The more we try to locate our position in the cosmic order, the more the ground shifts beneath us. We may not be the center, we may not be unique, we may not even be necessary. And yet, the very act of imagining these possibilities is a kind of defiance. It is not comfort we seek, but clarity. If the universe is a rare bloom in a field of lifeless variables, then to know it even briefly is to hold something sacred, even if that word belongs more to poetry than physics. There is a kind of quiet reverence in realizing that we live not under a dome of stars, but inside a storm of probabilities that, for a while, permitted reflection. The night sky is not a ceiling, but a question, and we are the echo of that question trying to answer itself. Somewhere, deep in the cosmic distance, a galaxy is vanishing, not because it is collapsing or consumed, but because the space between it and us is expanding faster than its light can travel. It continues to exist, burns with stars, carries the momentum of 1 billion years of history, but its story is now forever beyond our reach. The night sky, so vast and generous in our time, is slowly losing its memory. In the far future, this quiet disappearance will become the norm. Galaxies will drift beyond the cosmic horizon, leaving behind only the local group, those few dozen that remain gravitationally bound to us. Beyond that, silence will thicken. The cosmos will not end in a crash or a fire, but in a soft dimming, like the last embers of a great fire cooling into blackness. The stars will age. Red dwarfs, the most enduring, will flicker for trillions of years, but even they will one day exhaust their fuel. White dwarfs will cool into black cinders. Neutron stars will spin their last. Black holes, the most patient objects in existence, will slowly evaporate through Hawking radiation, particle by particle, until even their mass becomes memory. What remains will not be empty in the way we think of it. It will be thin, cold, and vast. A universe where energy is so diffuse that no new complexity can arise. A place where every possibility has already played out, and no reset is coming. This scenario, known as the heat death, is not merely a theoretical curiosity. It is a natural consequence of entropy, the tendency of energy to spread, of structure to dissolve, of time to move only forward. And yet, it is not entirely bleak. For in this long, slow twilight, meaning is not dictated by duration. It is forged in the moments where perception exists. In the rare span when stars burn and minds awaken, when questions are asked and answers sought not to dominate, but to understand. We are of this universe, not merely in it. Our atoms were fused in stars. Our thoughts are electrochemical echoes of ancient energy, rearranged by biology into something that can doubt and wonder. Even if our kind disappears, even if the species vanishes long before the last light fades, That we existed at all reshapes the universe's story. Perhaps this, too, is a kind of cosmological inheritance, that from the laws that shaped stars and galaxies, something arose that could look back at those laws in awe, not because we were intended, but because we became capable of interpretation. And in interpretation, there is agency. In wonder, there is resistance to silence. Even now, in this era where the universe is still legible, we begin to build instruments not just to look, but to listen more deeply. We send spacecraft beyond the reach of our sun, messages carved in gold and digital pulses, hoping that someone, somewhere, someday, might hear and reply. Not because we expect them to, but because we can. This act of asking across impossible distances, of waiting with no assurance, is the most human kind of hope. It is not naive. It is not desperate. It is simply the echo of awareness refusing to be still. If one day, on a world we'll never see, a mind will never meet points an eye at a cooling remnant and deciphers its origin, they will find traces of us in the dust, not as conquerors, not as footnotes, but as part of the unfolding a voice that rose briefly, and spoke, and listened, before returning to the dark from which it came.